Some folks get excited at the thought of traveling enormous distances in the blink of an eye. That's where warp drives step into the conversation. This idea is all about crossing space far faster than normal rockets could ever manage, almost as if you have your own shortcut through the cosmos. The basic notion of a warp drive involves bending the fabric of space itself. Instead of racing from point A to point B, you try to bring point B closer to you and then put it back where it was. It's similar to the old trick of folding a sheet of paper so two distant points meet. In theory, if you could warp space like this, you wouldn't be moving beyond the speed of light in the usual sense. You'd be using space itself to do the heavy lifting. Scientists discuss a special kind of energy or field that would be needed to pull off this amazing feat. They talk about something called exotic matter that might have truly unusual properties, like possibly having negative mass. But it's important to note this is all speculative. No one has produced or stored such matter yet, so no functional warp ship exists. So the concept is so captivating that researchers keep exploring it through math and computer models. An easy way to picture this is to think of space as a large rubber sheet, like a trampoline. You sit on one spot, and your friend sits on another spot far away. Normally, you'd crawl across the trampoline to reach them. But if you could stretch or contract the trampoline between you, you might pull your friend close almost instantly. That is basically the spirit behind warp drives. While the math and engineering remain beyond what we can achieve right now, the idea sparks hope that humans might one day zip around the galaxy as quickly as they do in certain science fiction stories. Until then, we keep studying, testing theories, and learning more about the nature of space and what might be possible in the distant future. Traversable wormholes. Plenty of people love the idea of stepping through a doorway and popping out light years away. That's the core concept of a traversable wormhole, a special tunnel that connects two points in space, or even time, so you can travel between them in a brief moment. You might think of it as a cosmic shortcut. Instead of taking the usual path, you slip into one end of the wormhole and appear at the other. A simple example would be if you draw two dots on a piece of paper. Normally, you just draw a line between them to show the distance. With a wormhole, you fold the paper so the dots line up, then poke a hole straight through. Where did the idea come from? It arises from the equations of Albert Einstein's general theory of relativity. This theory explains how mass and energy bend space. In some of those math solutions, you see shapes that look like tubes or tunnels, potential wormholes that connect different regions. But building a wormhole you could actually pass through is a huge challenge. Most calculations suggest you need exotic matter with negative energy to keep the tunnel open. Without it, the walls of the wormhole would pinch shut instantly. One comparison is a flexible straw. If you bend it too sharply, it crumples, and nothing can pass through. For a wormhole, negative energy acts like a brace to keep the tunnel open. The catch is that we don't know how to create or hold large amounts of negative energy, if it even exists in such a form. So, physicists continue to investigate strange quantum effects that might offer hints. What's the payoff if it works? You could move between distant stars or galaxies in almost no time, which would revolutionize space travel. It also leads to wild ideas about time travel. Since space and time are tied together, a wormhole might allow jumps into different eras, raising lots of philosophical and logical puzzles. For now, traversable wormholes remain in the realm of mathematical possibility and theoretical debates, but they give us a glimpse into just how weird and wonderful the universe might be. Tachyons. People often wonder if there's such a thing as speed beyond speed itself. Tachyons are a proposed kind of particle that always travel faster than light. The name comes from a Greek word meaning swift, and it's clear why. If these particles exist, they'd be zooming around at speeds no ordinary object could reach. In our everyday life, light itself is incredibly fast, taking just about 8 minutes to get here from the sun. According to physics, it's the ultimate speed limit for anything with mass. Tachyons, however, are imagined to be on the other side of that barrier. They'd start off faster than light and stay that way. Why would anyone propose such a wild idea? It appears in certain solutions to Einstein's special relativity equations. When you play around with the math, you find something called imaginary mass, which is a peculiar concept meaning the square root of a negative number shows up in the equations. This leads to the conclusion that if tachyons are real, they can never slow down enough to reach light speed because that would require infinite energy. They're locked into a realm beyond that speed limit, which is mind-bending to say the least. A rough analogy is imagining temperature. We know absolute zero is the coldest anything can get. Tachyons would be like a substance that's already beyond that limit, like a negative temperature situation where the usual rules don't apply. In other words, they're outside the normal range we can handle. Have scientists detected tachyons? So far, no. If any experiment had confirmed them, it would be front-page news. Some data in the past hinted at particles moving faster than light, but these were chalked up to measurement errors. Because no solid proof exists, tachyons remain purely hypothetical. So they fascinate physicists and dreamers because finding even a hint of them would flip our understanding of the universe. For now, tachyons serve as a reminder that our cosmic rulebook might have corner cases we haven't fully explored, keeping science ever open to new surprises. Negative Massachusetts. Sometimes, it helps to imagine a world where things push you forward when you try to pull them. That's the idea behind negative mass. We're used to everything having positive mass, which means they respond to pushes and pulls in the usual, predictable way. You shove an object, and it moves away in the same direction. Negative mass would flip that script. If you tried to push something with negative mass, it might accelerate in the opposite direction, toward you rather than away. This sounds cartoonish, but it shows up in certain physics equations under special circumstances. Why talk about negative mass at all? In advanced theories about the universe, and when discussing things like warp drives or wormholes, some scientists say you'd need a form of matter that behaves strangely, something with negative mass, to keep those exotic setups stable. For instance, a wormhole might collapse in on itself unless there's a repulsive, negative mass material holding it open. An easy analogy is to think about a shopping cart that insists on rolling the other way as soon as you push it forward. It's tricky to wrap your head around because it's so unlike normal experience. But that's the point. Negative mass stands outside the bounds of what we typically encounter. Have we found literal negative mass objects? Not exactly. However, there have been experiments with ultra-cold atoms or special quantum fluids that behave as if they have negative mass under certain conditions. It's not the same as finding a piece of solid material you can hold, but it suggests that these weird phenomena might be possible in very controlled environments. Whether a chunk of truly negative mass ever existed in nature remains unknown. So, the concept excites researchers because it represents how flexible the laws of physics can be. If negative mass could be harnessed, it might pave the way for new technologies or explain certain cosmic mysteries. Until then, it remains a fascinating hypothetical that challenges our most basic intuitions about how matter should behave. Alcubierre Metric. Long ago, a scientist named Miguel Alcubierre came up with a bold idea for faster-than-light travel. This idea is called the Alcubierre Metric, and it describes a kind of warp bubble that could ferry you across huge distances in a very short time. Instead of saying, "Let's go faster than light," it says, "Let's drag space itself around our ship so we don't break the speed limit locally." In simpler terms, you'd stay inside a cozy bubble of normal space, while the space in front of you gets compressed and the space behind you gets stretched out. This way, you could appear to travel faster than light without ever locally exceeding that limit. Why bother with such a concept? Einstein's laws tell us that no object can move through space faster than light if it has mass. But those laws don't forbid space itself from expanding or contracting at any rate. For instance, galaxies far away can seem to recede from us faster than light because the space between us is expanding. Alcubierre's genius was to apply that same trick on a smaller, more controlled scale around a spaceship. A handy analogy is a moving walkway at the airport, except instead of you walking faster, the floor shortens or lengthens under your feet to bring your destination closer. Now imagine you could control that process with a dial, adjusting how much the walkway stretches. That's sort of what the Alcubierre metric proposes, but it's far more complex mathematically. The catch is that you'd need something often referred to as exotic matter with negative energy density. We don't have that on hand. Even if we did, controlling it to form a stable warp bubble seems way beyond our current engineering abilities. Nevertheless, the Alcubierre metric has fired up imaginations in both science fiction and serious scientific circles, suggesting a loophole in the cosmic speed limit. While it remains theoretical, it shows how creative thinking can open new possibilities for interstellar exploration, reminding us that science can be just as daring as the best fiction. Casimir Effect. Every now and then, we spot something that reminds us empty space isn't truly empty. The Casimir Effect is a prime example. Take two uncharged metal plates and place them very close together in a perfect vacuum. No air, no dust, nothing. Even though there's nothing in between, these plates experience a slight force pulling them together. That's surprising, right? The simplest explanation is that quantum fluctuations in what we call empty space push them from the outside more than from the inside. Imagine the vacuum as having tiny waves or ripples of energy everywhere. Think of an ocean surface, where even on a calm day, you'll see small ripples. Between those two plates, only certain waves can fit. Fewer waves means less pressure inside. So comparatively, the plates get nudged together by the waves outside. This phenomenon, measured in labs, is proof that the vacuum has an underlying energy known as zero-point energy. This effect matters a lot in fields like nanotechnology, where surfaces are extremely close, and tiny forces can have big consequences. It also intrigues those who speculate about tapping vacuum energy for power, though we don't yet have a method to use it for large-scale energy production. A simple illustration might be two big boats floating on a calm lake. Waves can move around them on all sides, but if the boats are quite close, fewer waves can fit in between them, so they might be pushed together. The Casimir effect is the quantum version of that, on a scale far smaller than boats on water. Overall, the Casimir effect is a reminder that our everyday idea of empty is oversimplified. On tiny scales, the universe is alive with fluctuations and virtual particles that appear and disappear in fleeting moments. It's part of what makes quantum physics so fascinating. There's always more going on behind the scenes than we can see. Even the simplest vacuum can produce a measurable push or pull under the right conditions. Zero-point energy extraction. Now and then, you might hear about the possibility of tapping an endless energy source straight from empty space. That's the idea behind zero-point energy extraction. In quantum mechanics, even a system at its lowest possible energy state, where everything seems at rest, still has a little bit of energy left. We call this the zero-point energy. That means every nook and cranny in the universe, even a perfect vacuum, carries this energy at a fundamental level. If we could harness this energy in a big way, it might provide more power than any fuel we know. Some even dream it could help us zip across space without needing conventional rockets. But here's the catch. There's no known method to pull out that energy and end up with a net positive gain. According to our current theories, the process of extracting zero-point energy usually demands at least as much energy as you'd get back, if not more. So, You can't just pop a machine in your living room and expect free electricity. A simple comparison is a tightly stretched rubber band. Even when you don't see it moving, it holds tension. Zero-point energy is like that subtle tension in the fabric of reality. But turning that tension into constant usable power isn't straightforward. The Casimir Effect shows zero-point energy is real. Yet harnessing it for practical purposes remains a dream. People still explore the concept, partly because if there's even a tiny loophole, the payoff would be tremendous. It's important, though, to distinguish genuine scientific inquiry from fringe claims of infinite energy that aren't backed by proper evidence. For a technology to be viable, it has to stand up to repeated experiments and fit within the framework of well-tested physics laws. So, is zero-point energy extraction a path to the future or just a fascinating speculation? Right now, most mainstream scientists say it leans toward speculation. But the quest itself teaches us about how quantum fields operate and may open the door to other unexpected discoveries. In the meantime, zero-point energy remains a symbol of the universe's hidden richness, reminding us that what we call nothing could be richer than we ever imagined. Quantum teleportation. A few decades ago, the word teleportation mostly brought up images of sci-fi shows. Today, quantum teleportation is an actual research topic, though it's not like teleporting people or objects. Instead, quantum teleportation moves the state of a particle from one place to another. Put simply, that means you have a particle with certain properties over here, and you recreate those exact properties in another particle over there, using the weird rules of quantum mechanics. How do you make that happen? It's all about something called entanglement. You take two particles, often photons, and set them up so they're entangled, meaning measuring one influences the other, even across distance. Let's label them photon A and photon B. Keep photon A and send photon B off to a friend. Then you introduce a third photon, phone C, which holds the information or state you want to teleport. By doing a special kind of measurement on photons A and C, and sending that measurement result to your friend, they can tweak photon B so that it becomes an identical copy of what photon C was. A simple illustration is making a mold of a key. You're not sending the key itself, but the instructions on how to shape a new key so it matches perfectly. In quantum teleportation, you're transferring the exact quantum state, and once it's transferred, the original state is essentially gone. No cloning, no duplicates left behind. So, does this mean we can teleport humans? Not at all. People have trillions upon trillions of particles, each with complicated states. Plus, the process needs the original to be destroyed in the act of measurement, which wouldn't make for a fun trip. So, quantum teleportation is useful in cryptography and might help build next-generation computers that share quantum data across cities or even continents. In short, quantum teleportation won't beam you to a star system like in the movies, but it does let scientists do something once considered impossible: send the exact quantum fingerprint of a particle across distance. This opens up possibilities for incredibly secure communication and advanced quantum networks that may change the way we process and transmit information. Quantum entanglement. Every so often, we come across a discovery that really stretches our sense of what's possible. Quantum entanglement is definitely one of those discoveries. When two particles become entangled, usually through very precise experiments, they share a connection so that measuring one affects the outcome of measuring the other, no matter how far apart they are. Albert Einstein famously called this spooky action at a distance, because it felt like it violated the rule that signals can't travel faster than light. But there's a catch. You can't actually use entanglement to send messages at superluminal speed. That's because you have no control over what result you see when you measure the first particle. All you know is that the second particle's measurement will be correlated. Only when you compare results afterward, through normal, slower than light communication. Do you see the pattern? So, it's bizarre enough that it's puzzled scientists for decades. Think of two coins that start off in a paired state. When separated across the city, flipping one coin seems random, but the result links perfectly with the flip of the other coin in a way that defies ordinary expectations. It's not that one coin is physically telling the other how to land. Instead, the two coins share a deeper connection from when they were prepared together. That's a rough analogy, but it captures the tied-together flavor of entanglement. So, why is this big news? Entanglement is a cornerstone of quantum technology. It's how quantum computers can do certain calculations quickly by processing entangled bits, or qubits, in parallel. It's also crucial in quantum cryptography, ensuring ultra-secure communication. In a sense, entanglement shows that our universe allows events to be linked in ways classical physics never allowed. Scientists keep testing entanglement to see if there's a hidden explanation. But so far, each test reaffirms the quantum view. Nature is deeply interconnected at the smallest scales. It's one more reminder that the universe doesn't always follow the rules we expect from our everyday experiences, and that's what makes it so endlessly fascinating. Grandfather paradox. Occasionally, people wonder what would happen if time travel let us change the past. The grandfather paradox is the classic scenario for that thought experiment. Suppose you travel back to a time before your parent was even born, and you meet your grandfather in his youth. If you somehow prevent your grandparents from meeting, you'd never be born. That means you couldn't have traveled back in time in the first place. So how did you get there? This paradox isn't just playful imagination. It forces us to look at how cause and effect work. Normally, events move from past to present to future in a steady flow. If backward time travel existed, you'd risk breaking that chain. You would have an effect, you interfering, that leads to a cause, you never existing, which is a mind-bending loop. One idea some physicists and philosophers suggest is that the universe might protect its timeline. If you try something that would stop your own existence, something else intervenes, maybe a random event blocks your plan. Another approach says that if you do change the past, it spins off a new timeline or alternate reality, so your original timeline remains untouched. In that case, you're meddling with a parallel version of history, not your own. A handy analogy is trying to rewrite the first chapter of a book while you're in the middle of reading the last chapter. If you erase the events that set up the plot, how do you still have a story at all? That's essentially the grandfather paradox, but with real people and real events. Nobody knows for sure how time and causality would handle such a contradiction. That's why this paradox continues to show up in science fiction and deep philosophical discussions. It highlights the complexities of time travel theories, reminding us that our understanding of time as a simple, one-way arrow might be incomplete, or at least more flexible than we assume. For now, the grandfather paradox sits at the edge of what we know, urging us to keep questioning how reality really works if time travel were ever on the table. Closed time-like curves. What if the route to your next stop on the timeline was more like a loop than a straight line? That's the essence of closed time-like curves. In regular experience, time feels like it runs from the past into the future without turning back. But in certain theoretical solutions to Einstein's equations, you can find paths that loop back onto themselves in time. This means you could start off now, follow one of these loops, and end up in your own past. To picture it in simpler terms, imagine hiking on a trail that brings you in a big circle back to your starting point. That's pretty normal in space. Think of circular routes on a map. But it's much stranger if time is involved. You'd wind up meeting earlier versions of yourself or overlapping with events you already experienced. It's like reading a mystery novel where you can flip back to the first chapter as part of the storyline. Not just as a reader. Physicists get curious about whether these loops could exist in reality or if something prevents them. One argument is that nature somehow enforces causal consistency, meaning you can't produce paradoxes. Another viewpoint is that if these loops ever formed, they would demolish logical cause and effect. For example, if you popped back in time and taught yourself how to do something, who was the real teacher in the first place? Some exotic cosmic objects or rotating universes in theory might allow for closed time-like curves to appear. However, nobody has found a definite case in the actual universe. If it ever did occur, it would open the door to all sorts of contradictions, like the grandfather paradox, only on an even wilder scale. So, closed time-like curves aren't dismissed outright because they pop out of legitimate math that extends from Einstein's work. They remind us that time might be more flexible than we generally assume, even if they don't exist in everyday life. Exploring them helps us dive deeper into how space and time interweave, and how far we can stretch those concepts before they break. It's a perfect example of how theoretical physics can challenge our common-sense ideas and keep us curious about what lies beyond our current understanding. Gödel Universe. Try to imagine living in a universe that's always spinning like a cosmic merry-go-round. That's one way to explain what's called the Gödel Universe. Proposed by mathematician and logician Kurt Gödel, it's a peculiar solution to Einstein's field equations where space itself rotates. This rotation isn't like Earth spinning on its axis. Rather, the entire fabric of space-time has a swirl to it. Why does this matter? Well, in Gödel's model, there could be paths in time that loop back on themselves. If you follow a certain route through that swirling space-time, you might end up in your own past. It sounds like pure science fiction, but mathematically, the equations don't rule it out. Gödel was a genius at spotting paradoxes, and in creating this universe, he highlighted one in cosmology. Maybe the laws of physics allow for time travel under special circumstances. Think of a rotating universe like a giant rotating stage. If you walk across the stage in a straight line, you might find that the stage's rotation brings you back around to a point you've already visited. Now replace the stage with all of space-time, including time itself, and you get the mind-bending notion that traveling forward can circle around to an earlier moment in history. Of course, we don't see evidence that our real universe is spinning in this grand way. Observations of galaxies and cosmic background radiation suggest our cosmos is mostly uniform and not rotating on a huge scale. So, the Gödel universe might be a purely hypothetical setting, an alternate universe scenario that pushes theoretical boundaries. So, it's worth studying because it shows how flexible Einstein's equations can be. They don't necessarily force the universe to look the way ours does. That's part of what makes theoretical physics fascinating. The same fundamental rules can open doors to realities that seem more fitting for a wild sci-fi movie. Even if we never find a Gödel-like swirl in our cosmos, exploring it nudges us to ask deeper questions about time, causality, and how many different ways a universe could be put together. Exotic energy/matter. Picture a substance so strange that it pushes outward instead of pulling inward. This is the idea behind exotic energy or exotic matter. In ordinary life, we see gravity as a force that attracts. Planets tug on moons, and stars keep their solar systems close. But for hypothetical exotic matter, gravity could be repulsive. It's the ingredient many scientists think would be needed to hold a traversable wormhole open or to build a functioning warp bubble. A simple way to think about it is negative pressure or negative mass. Usually, mass is positive, meaning if you push it, it moves away from you. With negative mass, if you pushed it, it would accelerate in the opposite direction, sort of like a bizarre cartoon moment. Of course, nobody has actually observed a chunk of exotic matter in a lab, but quantum theories sometimes hint that very small amounts of negative energy might appear in fleeting quantum effects. Why does anyone believe in these odd concepts? When we do the math for wormholes or warp drives, like Alcubierre's concept. We keep running into the same requirement. We need a form of matter that behaves in ways normal matter doesn't. Without that, wormholes collapse instantly, and warp bubbles fizzle out. So, exotic matter is a placeholder for something that could keep these structures stable. Imagine trying to keep a tunnel from collapsing in a loose sand dune. You'd need strong supports to hold the sand back. Exotic matter is that support for the sand of space-time, preventing it from caving in. It's what you'd need to push the sides away. If we had enough of it, and if it worked exactly the way theories say, who knows? Maybe wormhole highways or warp travel could be possible. But let's be clear, this is still very speculative. Creating or detecting stable exotic matter in large amounts is beyond current technology. Some argue it might be impossible on practical grounds. Even so, exotic matter remains a hot topic in visionary physics, capturing our imagination with the promise of overcoming normal constraints and stepping into realms we once assumed were pure fantasy. Hawking radiation. Ever wondered if black holes can actually lose weight over time? According to Stephen Hawking's famous prediction, they can, by radiating energy in a process now called Hawking radiation. We typically think of black holes as cosmic vacuum cleaners that suck in everything. Once something crosses the event horizon, the point of no return, it's gone, right? But quantum physics throws a twist into that logic. Here's a simplified way to see it. Space, even empty space, never truly sits quietly. Quantum fluctuations create pairs of virtual particles that pop in and out of existence. Under normal conditions, these pairs cancel each other almost instantly. But near the event horizon of a black hole, one of the pair might fall in while the other escapes. It's like two skydivers joining hands in free fall. If one gets pulled away faster, the other is flung off. The escaped particle then appears as radiation coming from the black hole. This process robs the black hole of a tiny bit of its mass energy each time it happens. Though the effect is tiny for large black holes, over very long periods, they'd gradually evaporate. Imagine a slowly melting snowball in the sun, except the black hole is melting away by emitting these particles. A small enough black hole might vanish quickly on cosmic timescales, possibly ending in a burst of energy. Hawking's idea was groundbreaking because it brought together general relativity, which covers black holes and gravity, with quantum mechanics, the realm of particle physics. It suggested that black holes aren't total information graves, but rather have a subtle way of giving off energy. This revelation led to deep puzzles, like the black hole information paradox. If a black hole disappears, what happens to all the information about the stuff that fell in? In essence, Hawking radiation reminds us that black holes aren't as final as they seem. They're still an extreme environment, but they must play by quantum rules too. That bridging of theories is why Hawking radiation remains a central topic in modern theoretical physics, fueling our quest to unify gravity with quantum laws. Black hole starship. Imagine turning a tiny black hole into an engine for your spaceship. This might sound like something straight out of science fiction, but some physicists have looked into it as a far-future propulsion concept. The idea goes like this. If you create or capture a miniature black hole, it constantly emits Hawking radiation. That radiation could be harnessed to power and propel a spacecraft forward, much like how a nuclear reactor drives rockets in some theoretical designs. Think of it as a cosmic campfire. A black hole is so dense that its extreme gravitational field generates heat in the form of Hawking radiation. If you direct and channel that energy, you could, in theory, get thrust. Of course, there are mind-boggling challenges. First, you'd have to either make a black hole artificially, which seems nearly impossible with our current knowledge, or corral a naturally occurring tiny one without getting devoured. Then you'd need advanced materials that could handle the intense radiation without being vaporized. A good analogy might be harnessing the power of the sun. We do that on Earth with solar panels. But now imagine your sun is a minuscule black hole radiating energy in every direction. You'd need a clever design to convert that energy into useful motion. Some outlines of black hole starships suggest surrounding the hole with a parabolic reflector-like structure to direct the radiation backward, producing forward thrust. But it's worth noting that all this remains deeply speculative. Even if we solved the engineering hurdles, the question is whether the resources required to keep such a black hole stable and safely contained would outweigh the payoff. And if the black hole grows larger by consuming stray matter, it could pose serious risks to the craft and its crew. So, the black hole starship idea is a testament to human creativity in imagining future space travel. It shows how we might use extreme physics to tackle extreme distances. After all, if we ever want to cross interstellar or intergalactic spans, we need to think far outside the box. For now, it's a captivating concept that stretches the limits of what we think is possible in propulsion. Dyson Spheres. Think about building a gigantic structure all around a star to capture every bit of energy it emits. That's the core idea behind a Dyson sphere. Imagine placing massive panels or entire habitats so they encompass the star, harvesting its light and heat from all angles. Freeman Dyson proposed the concept as a way an advanced civilization could meet its enormous energy needs, far beyond what a single planet could provide. A relatable analogy: if you've ever stood around a campfire in a big group, you'll notice folks shift positions to find the warmest spot. But a Dyson sphere is like encircling the entire campfire with a solid ring or sphere so that none of the fire's warmth escapes. On a grand cosmic scale, the fire is a star, and the circle is an enormous shell of solar collectors, orbiting at just the right distance. There are variations on this idea. A Dyson swarm would be many individual satellites orbiting in a cloud around the star, each collecting energy. A Dyson bubble might be a shell made of lighter materials, held in place by solar sails. Building a solid Dyson sphere with today's understanding seems almost impossible because the materials required to withstand gravitational and thermal forces would be extraordinary. Plus, you'd need more building matter than is found on many planets combined. So, Dyson spheres are a fun thought experiment for how an extremely advanced civilization, sometimes called a Type II civilization on the Kardashev scale, could harness the full power of their star. Some astronomers even look for signs of Dyson spheres around distant stars, speculating that if aliens have built one, it might alter the star's light in detectable ways. While we're far from building anything like this, thinking about Dyson spheres pushes us to consider the future of energy use. As our own civilization grows in energy demands, solar power becomes increasingly appealing. Maybe one day, in the distant future, our descendants will gather enough resources and technology to construct vast structures in space. For now, the concept broadens our perspective on what's possible and encourages us to dream big when we talk about cosmic engineering. White holes. Picture a black hole's polar opposite. Instead of dragging everything in, it spits everything out. That's the notion behind a white hole. In a black hole, once you cross the event horizon, there's no escape. But a white hole is often described as a region from which things can emerge, but nothing can enter. It's like a one-way exit door in the cosmic cafeteria. Stuff only goes out, never in. Mathematically, a white hole can appear as a valid solution to Einstein's equations if you treat time in a certain way or consider a black hole in reverse. Some even propose that the Big Bang itself might have been a white hole explosion, releasing an immense amount of energy in one instant. However, we've never seen a white hole in nature. They could be purely theoretical or might require special conditions that never arise naturally. One lighthearted analogy is a wind tunnel where air constantly blasts out but never gets sucked back in. But in normal reality, That's not how gravity works. Gravity is all about pulling objects together. For a white hole, you'd need a mechanism that forever prevents anything from falling in, which seems to conflict with what we observe in the universe. So, white holes show up in research papers and discussions about quantum gravity and the fate of black holes. Some theories suggest that when a black hole dies through Hawking radiation, there might be some kind of rebound effect, a sudden transformation into a white hole. It's highly speculative, but it's a way of saying maybe the matter swallowed by a black hole eventually gets released back into the universe in a big burst. For now, this idea rests on the fringes of physics, with no direct evidence. Regardless of whether white holes exist or ever did, they stretch our imagination about how extreme gravity can behave. They also open up intriguing questions about information flow in the universe. If black holes lose mass over time, might they transform and blow out the old contents? While that remains unproven, white holes at least expand our sense of cosmic possibilities, reminding us how much we have yet to learn about the deep workings of space and time. Advanced field propulsion. Imagine zooming through space not by igniting fuel, but by manipulating the fields around you, like gravity or electromagnetism. That's the broad goal of advanced field propulsion. Traditional rockets rely on throwing mass out the back, exhaust, to push the craft forward. But these futuristic concepts look for ways to harness force fields to glide, hover, or accelerate through the cosmos without lugging massive fuel tanks. A simple analogy might be how a surfer rides ocean waves. The surfer isn't carrying a motor. Instead, they make use of the wave's motion. In advanced field propulsion, the dream is to do something similar with gravitational or electromagnetic fields, letting them propel you where you want to go. If you could generate or modify these fields on command, you might accelerate without expending propellant. One famous example people discuss is gravity control, where you'd somehow create a localized distortion in space-time that pulls or pushes you around. Another approach might be using intense magnetic fields to repel against planetary or solar magnetic fields. So far, these remain mostly in the realm of theoretical ideas. We know how to generate strong electromagnetic fields, but harnessing them for large-scale propulsion in a vacuum is a tall order. And controlling gravity directly is something we simply don't know how to do yet. So, advanced field propulsion captures our imaginations because it promises a radical shift in how we explore space. If you're not tied down by how much fuel you can carry, you might undertake longer missions at higher speeds. It also offers a clue toward the kind of technology a very advanced civilization could use, where spaceships gently hover and accelerate without visible engines. We're not close to this future yet. Most of the research sits at the intersection of speculative physics and engineering. But even if just a fraction of these concepts pan out, they could revolutionize travel across the solar system and beyond. For many, advanced field propulsion is a holy grail of space exploration, an elegant solution that might lie just beyond our current understanding, beckoning us to keep pushing the boundaries of science. Quantum vacuum thrusters. Can you get something out of nothing? That question comes up when people talk about quantum vacuum thrusters. The basic claim is that by bouncing microwaves inside a specially shaped cavity, you might interact with the quantum vacuum in a way that generates thrust. At first glance, this sounds like sci-fi wishful thinking because you're not throwing mass out the back, which goes against the usual conservation of momentum principle. A rough comparison is imagining you're inside a car with the windows up, trying to push the car forward by shoving the dashboard. Normally, that shouldn't work because every action has an equal and opposite reaction. But proponents suggest that because the quantum vacuum isn't truly empty, there might be a way to push against the fluctuations that pop in and out of existence. It's a bit like claiming you've discovered a new frictionless surface to push against. Experiments with devices like the M-Drive, generated headlines a few years back, claiming small positive results. However, many in the scientific community remain skeptical. They suspect measurement errors, experimental setup flaws, or overlooked sources of interference could be the cause of any apparent thrust. Repeated attempts to verify these findings under more controlled conditions have largely failed to produce conclusive proof of real thrust. So, people keep testing the ideas because if it worked, the payoff would be enormous. Near fuel-free propulsion, making space travel far cheaper and more accessible. Whether quantum vacuum thrusters are impossible or just super difficult remains an open question. Mainstream physicists generally say the concept doesn't align with known laws, and extraordinary claims require extraordinary evidence. That's a standard motto in science. You must prove unusual ideas with strong, repeatable data. But the conversation itself is helpful. Even when an experiment yields zero results, it forces researchers to refine their methods and deepen their understanding of the quantum world. In that sense, quantum vacuum thrusters are a reminder that we still have a lot to learn about how quantum fields might be harnessed, and that every so-called impossible idea deserves at least a careful look before we fully rule it out. Mach's principle. Have you ever thought about what gives mass its inertia? Mach's principle proposes that the inertia of an object, its resistance to changes in motion, depends on the presence of all the other mass in the universe. In other words, how an object moves or stays still is influenced by the distant stars and galaxies around it, not just its immediate surroundings. It's like saying you can't truly define movement or rest unless you look at everything else out there. Imagine standing on a spinning merry-go-round. You feel the outward force pushing you away from the center. Mach's principle suggests that this sensation might be tied to the gravitational pull of all matter in the cosmos. If the universe were empty, no stars, no galaxies, would inertia even exist? According to Mach's thinking, perhaps not. Albert Einstein was intrigued by this notion when he worked on general relativity. Although Einstein's final equations didn't fully incorporate Mach's principle, the idea still inspired him. Today, some alternative gravity theories try to weave Mach's principle into their frameworks. The concept also plays a role in philosophical debates about absolute motion versus relative motion. Are you ever truly at rest? Or are you only at rest relative to something else? A simple analogy is fishing in a vast lake. The water around your boat seems to define whether you're moving or not. Yet, you're also part of a bigger environment. There are waves, currents, and the edges of the lake. The total effect of this entire body of water helps determine how your boat behaves. Mach's principle is like that, but with the mass distribution of the entire universe playing the role of the water. At present, we don't have a definitive, testable model that conclusively shows Mach's principle in action. So, it remains an intriguing viewpoint, reminding us that seemingly isolated properties, like how heavy something feels to move, could be tied to the grand tapestry of the cosmos. In a way, it's a beautiful idea that underscores the interconnectedness of all matter, reinforcing that our local experiences might be woven into the broader cosmic stage. Retrocausality. Could the future influence the past? That's the startling question at the heart of retrocausality. Normally, we picture cause and effect in a neat order. You drop a glass, cause. It shatters, effect. Retrocausality flips that sequence, suggesting an effect might happen before its cause, at least in certain quantum scenarios. This challenges our everyday sense of time as a one-way street. Think about a detective story. Usually, you have clues, effects, pointing to a crime that happened earlier, the cause. With retrocausality, it's as if a clue might appear before anyone ever commits the crime. It's so mind-bending that many physicists approach it with caution. But a few interpretations of quantum mechanics, especially those looking for ways around spooky action at a distance? Say maybe the future measurement can subtly shape the past state. One of the areas where retrocausality crops up is in the study of entanglement. Instead of faster-than-light signals connecting two particles, some argue the measurement outcome travels backward in time to correlate the results. This is still a minority view, and it's debated heavily. Conventional quantum physics can explain entanglement without resorting to retrocausality. However, the concept remains on the table as a possible way to interpret bizarre experimental data. A friendly analogy might be a video game that's partially loading the environment based on your future moves. If you decide to go left at a fork in the road, the game was prepping that area before you even got there. If that's how reality worked, your future choice would feed back into the present somehow. Does that mean you can fix mistakes you made in the past by sending a message back in time? Probably not. Even the wildest retrocausality theories are subtle and don't allow big, noticeable changes to history. More likely, it happens on tiny quantum scales, woven into probabilities and outcomes that we rarely sense in everyday life. While retrocausality remains speculative, it's a reminder that time might be more flexible than we assume. By probing the boundaries of cause and effect, scientists hope to refine our understanding of quantum mechanics and maybe discover a deeper layer of how the universe truly operates. Antimatter propulsion. Think about a rocket fuel so potent that a tiny amount could outmatch entire warehouses of chemical propellant. That's the promise of antimatter propulsion. Antimatter is like the mirror image of normal matter, same mass but opposite charge. When matter and antimatter come into contact, they annihilate each other completely, releasing a huge amount of energy, often in the form of gamma rays. For a quick illustration, imagine mixing baking soda and vinegar, but multiply the reaction's intensity by 1 billion times or more. Antimatter annihilation is one of the most energetic processes known, so if you could harness it, you'd have an incredibly efficient rocket engine. A small stash of antimatter could, in theory, propel a spacecraft to fractions of the speed of light, slashing travel time to distant planets or even nearby stars. The challenge? Antimatter is extraordinarily rare in nature. We make tiny amounts in particle accelerators, but producing just micrograms costs enormous amounts of energy and money. Then, once you have it, you have to store it in magnetic or electromagnetic traps so it never touches the container walls of normal matter. Even a tiny slip-up, and poof, it's gone in a flash of gamma rays. That's like trying to store live fireworks in a paper bag while you juggle them. Some futuristic designs picture a spacecraft that drips a controlled amount of antimatter onto a reaction mass, like normal hydrogen, to get a steady thrust. Others imagine using antimatter to trigger small nuclear explosions for a pulsed rocket. But these remain theoretical blueprints until we can produce and store enough antimatter safely. While the challenges are huge, so is the potential payoff. If humans ever hope to explore beyond our solar system in a reasonable time frame, we need propulsion methods that greatly exceed chemical rockets. Antimatter offers a glimpse of what might be possible if we perfect advanced technology. Right now, it's an ultra-expensive, highly volatile substance we can only create in minute quantities. But who knows, if our understanding and engineering abilities keep growing, antimatter propulsion might one day shift from science fiction to a daring reality. Gravitational wave communication. What if you could send messages through ripples in space-time itself? That's the concept behind gravitational wave communication. We're used to sending signals by radio waves, microwaves, or lasers, all of which are electromagnetic. But gravitational waves are entirely different. They're disturbances in the fabric of space-time, traveling outward from massive accelerating objects, like merging black holes or neutron stars. After decades of searching, Detectors like LIGO finally confirmed gravitational waves in 2015. However, these waves are extremely faint by the time they reach Earth. That makes them very hard to detect, let alone produce on demand. The idea that you could manipulate masses in a precise way to encode information in gravitational waves intrigues some scientists. If it were possible, you might broadcast signals that pass through anything, stars, planets, entire galaxies, without much weakening. Think of it as a super-penetrating phone signal that doesn't care about walls or distance. In principle, gravitational waves can travel unimpeded across cosmic scales. If an advanced civilization mastered the art of generating them, they might set up a gravitational wave radio that beams messages across the universe. We'd need staggeringly large masses and energies to do it, maybe by spinning or smashing huge objects in carefully planned patterns. For a down-to-earth analogy, imagine trying to signal a friend by creating ripples in a solid floor, hoping the vibrations travel all the way to them, even if there's furniture or walls in the path. That's basically gravitational wave communication, except the floor is the geometry of space, and the objects generating waves are far more massive than anything we can handle. So, is this technology feasible for humans? Not with current methods. Our gravitational wave detectors need colossal events in deep space to pick up even a tiny signal. But the concept sparks curiosity about how advanced civilizations might communicate or how we might do it in the distant future. The more we learn about gravitational waves, the more we realize they might hold potential for new forms of astronomy and communication, if only we can figure out how to harness them effectively. Femtotechnology. Have you heard of nanotechnology, which operates on the scale of atoms and molecules? Now shrink that idea even further to femtotechnology, dealing with structures at the scale of femtometers, 10 to the power of -15 meters. At that size, you're no longer talking about manipulating atoms, you're dealing with the inner building blocks of protons and neutrons, or even quarks themselves. A helpful analogy is to imagine slicing a single grain of sand into a million little pieces. That's kind of what nanotechnology does to everyday objects. But femtotechnology is like slicing even those pieces thousands of times more. The fundamental forces inside atomic nuclei are enormously strong, which means controlling quarks or gluons is far more challenging than controlling chemistry. In chemistry, electrons can be shared or moved around. But in femtotechnology, you'd have to tweak the strongest force in the universe, the strong nuclear force. Why would anyone consider such a thing? If it were possible, you might engineer exotic forms of matter that are more stable or have unique properties. Maybe you could build strange matter, a hypothetical substance made of strange quarks that could be incredibly dense and powerful. Such materials, if they exist, might offer breakthroughs in energy storage or super-strong construction. However, all this is purely speculative right now. We can't reliably manipulate quarks in stable, large-scale structures. Think of it like being a jeweler who can shape precious metals into intricate designs, except now you're trying to craft jewelry out of the nucleus itself. The tools and processes needed are beyond our current grasp. Particle accelerators can smash protons apart for fleeting moments, but building stable, engineered structures is another matter entirely. Whether femtotechnology will ever be more than a futuristic dream is up in the air. Even so, it expands our horizons for what advanced civilizations could accomplish. If humankind ever developed the means to manipulate quarks as easily as we handle electrons, it might open up unimaginable avenues for technology. For now, it remains a mind-boggling concept that underscores just how vast the frontier of science can be, even as we burrow down into the tiniest known scales of reality. Planck energy experiments. Ever thought about cranking particle accelerators to such extremes that you reach energies on the Planck scale? That's the concept behind Planck energy experiments. The Planck energy is about 10 to the power of 19 gigaelectronvolts, trillions of times higher than what our current accelerators can produce. At these wild energies, the usual distinctions between quantum mechanics and gravity might blur, offering a direct peek into a theory of quantum gravity. A quick analogy is hitting a piñata with increasing force. At low taps, you see small effects, maybe a few cracks. Increase the power, and eventually, you break it open completely, revealing what's inside. With the Planck scale, you'd be smashing space-time at such intensity that it might break your everyday assumptions, exposing new physics. Some believe that at or near the Planck energy, you could see tiny black holes forming, or detect new fundamental particles that unify the forces of nature. Why does this matter? Our best theories, general relativity and quantum field theory, struggle to merge smoothly. Near the Planck scale, we think quantum gravity effects become huge, so experiments there could reveal how space-time and particles truly mesh. It might confirm concepts like string theory or point to entirely new frameworks. Of course, generating Planck energy collisions is almost beyond imagination today. The Large Hadron Collider is powerful, but still minuscule compared to what you'd need. You'd likely require a device the size of a solar system or some cosmic event to get close to those energies. Cosmic rays sometimes arrive with extremely high energies, but capturing and analyzing them precisely is another challenge. Despite the technical hurdles, theorists keep dreaming of Planck energy experiments because they could unlock secrets about the early universe, when all matter and energy was in a superdense, ultra-high energy state right after the Big Bang. Studying that regime might help us understand dark matter, dark energy, and why our universe looks the way it does. So, while we won't be building a Planck-scale accelerator anytime soon, the idea keeps scientists motivated. It's a marker of how far we might go if technology keeps advancing. And it's a reminder that the ultimate building blocks and laws of the cosmos might reveal themselves only when we push physics to its absolute extreme limits. Quantum gravity. There's a deep puzzle in modern physics about how to make gravity fit together with quantum mechanics. That puzzle goes by the name quantum gravity. At one level, we have Albert Einstein's general relativity describing how massive objects curve space-time and create what we experience as gravity. On the other level, there's quantum mechanics, which explains the strange, probabilistic behavior of particles at very small scales. Each theory excels in its own domain, yet they don't blend smoothly into one unified framework. That's the core issue quantum gravity aims to solve. One way to look at it is thinking about water and oil in a glass. Both are liquids, each with its own properties, but they don't mix into a single, consistent fluid. Similarly, relativity and quantum mechanics remain separate fluids of knowledge that, so far, resist merging into one. Many approaches attempt to tackle this challenge, including string theory and loop quantum gravity. String theory suggests that everything is made of tiny vibrating strings, while loop quantum gravity focuses on space-time itself, describing it as woven from discrete loops. Why does any of this matter? Because at extremely high energies or very tiny scales, like near the center of black holes or right after the Big Bang, both quantum effects and intense gravity come into play at the same time. Our current theories can't give us a complete picture of what happens there. Understanding quantum gravity could reveal entirely new insights into how the universe began, how black holes really behave, and maybe even how time fits into the grand scheme. Practical experiments aren't easy to design because the energies needed to see quantum gravity effects are enormous. So, researchers keep looking for subtle hints in cosmic observations or from advanced experiments here on Earth. While it remains one of the biggest unsolved problems in physics, Quantum gravity represents a frontier that might one day unify two pillars of science into a single, beautiful theory. If that day comes, it could rewrite our understanding of reality, opening the door to possibilities we haven't even dreamed of yet. Variable speed of light. There's a well-known saying in physics: the speed of light in a vacuum is constant, around 300,000 kilometers per second. That idea underpins Einstein's special relativity. But a few theories ask a bold question. What if the speed of light wasn't always constant in the universe's history or under certain extreme conditions? This is the heart of variable speed of light, VSL, theories. In most everyday situations, light does slow down when passing through materials like water or glass, but that's not what VSL is about. VSL suggests that even in a true vacuum, the fundamental constant we call C might not be so fixed after all. Advocates of these theories say it could explain puzzles like why the universe looks so uniform in all directions. Normally, inflation theory addresses this, but VSL offers a different approach. If light could travel faster in the early universe, distant regions would have more time to share information, creating a uniform temperature. To visualize it in simple terms, picture a group of runners starting a race at different points on a track. If some can sprint faster than normal at the very start, they might meet up and chat, ensuring they coordinate. Then, once the boost period ends, they go back to regular speeds. By the time we see them, they look in sync, though they began from scattered positions. VSL theories remain speculative, and many physicists hold that the constancy of light speed is too central to modern physics to break. After all, it's woven into relativity and underpins much of our precise GPS and satellite technology. Changing it could create more complications than it solves. Nonetheless, some researchers keep exploring the math, looking for observational tests that might confirm or refute the possibility. For instance, they might study light from the early universe, encoded in the cosmic microwave background, for tiny deviations that suggest light once moved at a different speed. Though not mainstream, the variable speed of light idea demonstrates how physicists sometimes challenge even the most hallowed principles when searching for clues to cosmic mysteries. It's a reminder that no law is entirely off-limits to reconsideration if it might unlock a deeper understanding of why the universe is the way it is. Space-time crystal. There's a fascinating concept that takes the idea of crystals one step beyond 3 dimensions. A space-time crystal. In a normal crystal, atoms line up in a repeating pattern in space. With a space-time crystal, that repetition would extend into the time dimension as well, creating a structure that repeats itself periodically, forever. To make this easier to grasp, think about a simple music box. It repeats the same tune over and over, cycling through a set arrangement. A space-time crystal is like that tune, but on a fundamental physical level. The system keeps looping through a series of states, never settling down into a single, static equilibrium. Even if you leave it be for a very long time, it keeps cycling with a perfect rhythm. Scientists first proposed the notion in 2012, and since then, experimental versions have been made using quantum systems where particles interact in a way that allows for a time-based periodicity. They're often called time crystals. The practical method involves driving a set of atoms with lasers or microwaves and using quantum effects to lock the system into a repeating pattern. Essentially, it's as if the entire group of atoms is dancing in perfect sync indefinitely. Why is this interesting? Because it challenges the usual idea that a system at its lowest energy state, its ground state, must be static. A time crystal suggests you can have motion without using extra energy in the conventional sense, an ongoing periodic change that doesn't wind down. That's a bit like having a pendulum that never slows down, even though it's not being pushed. Practical applications aren't entirely clear yet, but researchers see potential for precision measurement or quantum computing. Time crystals might offer new ways to store quantum information or keep it stable against external noise. At the very least, they open a door to new phases of matter we never thought possible. As these experiments advance, space-time crystals stand as a striking example of how our universe can surprise us with forms of order that defy everyday intuition, reminding us there's always more to discover at the frontiers of physics. Rotating black holes, Kerr black holes. There's a type of black hole that puts on a cosmic show by spinning so fast it drags space-time around with it. These are known as Kerr black holes. Unlike the simpler, non-rotating Schwarzschild black holes, Kerr black holes have an ergosphere, a region outside the event horizon where space is pulled along in the same direction as the black hole's spin. If you ventured there, you couldn't remain still relative to a distant observer because the fabric of space-time itself is rotating. An analogy to help visualize this is a whirlpool. In a calm pond, water sits mostly still, but in a whirlpool, anything nearby gets swept around in a circular motion. The rotating black hole does something similar with space-time, creating a frame-dragging effect. This phenomenon is so intense that, in principle, you could dive into the ergosphere and somehow steal energy from the black hole's rotation, a process called the Penrose process. It's like tossing a ball into the whirlpool in just the right way, retrieving it with more energy than it had going in, courtesy of the black hole's spin. Kerr black holes are fascinating because they're likely the real-world norm. Most stars rotate before they collapse, so the black holes they form probably retain that angular momentum. Observations of X-ray emissions around suspected black holes often point to significant spin rates. This spin also affects how matter spirals in. It can create impressive jets of high-energy particles shooting out from the black hole's poles, fueled by the disk of superheated gas around the event horizon. Beyond their astrophysical importance, rotating black holes present a rich playground for theorists. Some exotic ideas involve using the strong frame-dragging regions as a pathway to unusual time-like loops or shortcuts in space-time, though these remain highly speculative. Studying Kerr black holes helps us test general relativity in extreme conditions, offering insights into how gravity operates when things get incredibly dense and dynamic. In the end, Kerr black holes are like nature's cosmic merry-go-rounds, spinning with unimaginable energy. They stand as reminders that black holes aren't just static holes in space but vibrant, rotating giants that shape their surroundings in powerful and often surprising ways. Negative energy density. There's a curious idea in physics that space could hold forms of energy that tip below what we usually call zero. That's known as negative energy density. While it sounds odd, scientists have found hints of such possibilities in certain quantum phenomena, like the Casimir Effect, where the energy between two closely spaced plates can be lower than the surrounding vacuum. In everyday life, positive energy dominates, food fuels us, the sun radiates warmth, and so on. Negative energy, however, behaves in ways that defy our usual intuition. For example, it might produce a gravitational repulsion rather than attraction, which leads to talk about its uses in concepts like wormholes or warp drives. The idea is that if you could surround a region of space with negative energy, you might prop open a wormhole or push space-time in the odd ways required for superluminal travel. A simple analogy might be a bank account that can go below zero into overdraft territory, but in a strange twist, the more negative your balance, the more it repels future debts. Of course, money doesn't literally do that, but it illustrates how negative values can behave differently from positive ones. Finding enough negative energy for a practical purpose remains a towering challenge. In quantum field theory, negative energy densities typically pop up for very short times or in minuscule amounts that are difficult to sustain. Even if you generate it, you'd have to keep it stable, preventing it from flipping back to a normal, Positive energy state. The engineering hurdles are enormous. Despite these challenges, negative energy density is a cornerstone of many speculative ideas about advanced propulsion and exotic space-time geometries. Some researchers keep working on how it might be formed, or amplified, if at all possible. Even if we don't get a warp drive out of it, exploring negative energy deepens our grasp of how quantum fields and gravity might interact. At the very least, it keeps our minds open to the fact that there may be more to nothingness than we typically assume, hinting that the vacuum itself is far more dynamic than meets the eye. Artificial gravity. There's a cool idea for long-duration space travel where you don't float weightlessly all the time. Artificial gravity. In space, astronauts deal with microgravity, which affects their bodies. Bones lose density, muscles weaken, and fluids shift. Artificial gravity aims to mimic Earth's pull so people can live more normally in orbit or on interplanetary journeys. One popular approach is rotation. If you spin a spacecraft, the centrifugal force can push objects outward against the hull, creating a sensation similar to gravity. Picture a rotating theme park ride. When it spins fast, you feel pressed against the wall. A rotating space habitat could use the same principle. The bigger the station, the slower it needs to spin to produce comfortable gravity without causing motion sickness. That's why many sci-fi movies show massive rotating rings or cylinders in space. Another concept involves constant acceleration. If a spaceship continuously accelerates at 1g, the gravitational acceleration on Earth, halfway to Mars, then flips and decelerates at 1g the rest of the way, you'd have artificial gravity the entire trip. However, this requires huge amounts of energy and fuel, making it challenging with current technology. Why care so much? Because living in 0g for months or years is tough on the human body and mind. Astronauts spend hours each day exercising to combat muscle and bone loss. With artificial gravity, they might skip much of that, potentially improving overall health and reducing the risk of complications upon returning to Earth. Of course, designing rotating habitats or building advanced propulsion systems is no small feat. The engineering is complex, and there are many trade-offs. A spinning station has to be sturdy enough to handle stress and large enough to minimize dizzying effects. So, we see prototypes or partial experiments, like short-radius centrifuges for research, which might pave the way for future developments. For now, artificial gravity stands as a tantalizing solution to the fundamental challenge of long-term human space travel. It's a testament to our desire to make the cosmos not just a place we can visit, but somewhere we can comfortably live, even if we have to spin our way to feeling at home among the stars. Inertial dampeners. There's a familiar trope in sci-fi. A spaceship accelerates to incredible speeds or makes sharp turns, yet the crew barely feels a bump. The explanation they give is typically inertial dampeners. These hypothetical devices would counteract the forces of rapid acceleration or deceleration, preventing passengers from getting squished. In real physics, high acceleration can be deadly. If you go too fast, your body can't handle the g-forces. But inertial dampeners, if they existed, would neutralize those effects. Think of driving a car. If you slam on the brakes, you and the passengers are thrown forward. Your seatbelt catches you, but you still feel that jolt. Now imagine a system that detects the deceleration and instantly applies an equal and opposite force on your body to cancel out the inertia. You wouldn't even lurch forward. That's the essence of an inertial dampener. In actual science, we don't have a mechanism to do this on large scales. There's no known way to negate inertia outright. Inertia is a fundamental property of mass, linked to Mach's principle and possibly to deeper quantum fields we don't fully understand. Some have toyed with advanced field propulsion ideas or negative mass concepts that might replicate an inertial dampening effect. But these are highly speculative. If inertial dampeners were real, they'd revolutionize everything from fighter jets to roller coasters. You could accelerate from 0 to supersonic speeds in seconds without experiencing so much as a nudge. It's a dream come true for extreme transportation, allowing rapid maneuvers and unprecedented travel possibilities. Despite the sci-fi tag, the inertial dampener concept pushes us to think about controlling forces on a profound level. It ties into fundamental questions like, can we directly manipulate mass, inertia, or space-time around us? Could advanced physics provide a method to offset those punishing g-forces? For now, inertial dampeners remain a plot device in movies and books. So they reflect the ongoing human desire to master motion so thoroughly that we can dance among the stars without feeling a single bruise. Faster-than-light neutrinos. A while back, a surprising announcement claimed that neutrinos, tiny nearly massless particles, had been measured traveling faster than light. Scientists at the Opera experiment in Italy reported this unexpected result, sending shockwaves through the physics community. The speed of light is the cosmic speed limit, so any confirmed evidence of faster-than-light travel would upend Einstein's special relativity. Shortly after, extensive checks revealed the cause: a faulty connection in the experiment's timing mechanism. Once fixed, the neutrinos' measured speed aligned with the speed of light. As expected, this was a classic example of science in action. Extraordinary claims require extraordinary scrutiny. Researchers thoroughly investigated every possible source of error, eventually finding a mundane technical glitch rather than a revolution in physics. So, the story of the faster-than-light neutrinos offers a window into how science works. When unexpected results appear, they must be replicated or confirmed by independent measurements. It also highlights how delicate the process of measuring neutrino speeds can be. Neutrinos rarely interact with matter, so detecting them requires large underground detectors, with precise timing systems to track their flight from creation points, often nuclear reactors or particle accelerators, over hundreds of kilometers. Could neutrinos ever exceed light speed in some other context? Theoretical possibilities like tachyons come to mind, but no concrete evidence supports that. Neutrino oscillations, where one flavor changes to another, are already a major discovery, showing neutrinos have mass, but that mass is still tiny. If they traveled faster than light, it would pose profound challenges to established physics, implying potential causal paradoxes or the necessity for new frameworks entirely. The faster-than-light neutrino case ended up reinforcing, rather than refuting, Einstein's limit. The episode remains a famous reminder that breakthroughs can sometimes be illusions born of equipment hiccups, and that robust scientific inquiry demands patience, collaboration, and a willingness to accept when data needs more scrutiny. Even so, it briefly lit up imaginations worldwide, proving once again how eager we are to explore the possibility that our deepest physical laws might still hold surprises. Pilot wave theory. There's a lesser-known interpretation of quantum mechanics called pilot wave theory or de Broglie theory. It challenges the mainstream Copenhagen interpretation by suggesting particles do have definite positions and momenta, guided by a pilot wave. Instead of wave functions collapsing upon observation, the wave is always there, and the particle moves in a trajectory influenced by it. Try picturing a surfer riding a wave. The wave dictates how the surfer glides forward. In pilot wave theory, the quantum wave function acts like that guiding wave. The particle is the surfer, carried along by the shape of the wave. Unlike the usual quantum viewpoint, where particles don't have a well-defined path until measured, pilot wave theory says there's a hidden, definite path, just hidden by the complexities of the wave function. Some people like this interpretation because it removes the need for wave function collapse. making the universe deterministic under the hood. But critics argue that pilot wave theory becomes quite complicated when dealing with multiple particles. The pilot wave extends into a very high-dimensional space, making it less intuitive. Also, it's not simpler than standard quantum mechanics in terms of mathematics or predictions. In fact, both pilot wave theory and the Copenhagen approach yield the same experimental results, so you can't pick one purely by measurement outcomes. Even though it's not the most popular viewpoint, pilot wave theory garners interest because it offers a real attempt at a more classical explanation of quantum phenomena, one where weird results like the double-slit experiment are explained by a guiding wave rather than a wave-particle duality that collapses unpredictably. Modern developments, like experiments with walking droplets on vibrating fluids, sometimes produce pilot wave-like patterns, sparking further curiosity. However, whether pilot wave theory will ever overthrow or complement the mainstream quantum picture remains an open question. It demonstrates that quantum mechanics isn't just a set of equations but a set of interpretations, each wrestling with mysteries like measurement, randomness, and reality. The pilot wave approach is one such wrestling match, keeping the conversation lively about what quantum theory truly says about the nature of things. Quantum computing for time travel. There's a mind-bending idea that quantum computers might one day simulate scenarios involving time travel or even help crack the logic behind it. While it sounds like something out of a sci-fi plot, the link between quantum computing and time manipulation emerges from thought experiments on closed time-like curves and quantum information. In essence, certain theoretical models suggest that if a quantum computer gained access to a loop in time, it could solve problems far beyond the capability of normal machines. Think of an impossible jigsaw puzzle. Normally, you try piece after piece, possibly spending hours. A quantum computer with a time loop might feed partial solutions back to an earlier moment, effectively reusing computations. This cyclical advantage could solve complex puzzles in no time. Of course, that's deeply hypothetical. We have no evidence such loops exist or that we can harness them for computation. Yet, even without actual time loops, quantum computers can do remarkable tasks, such as breaking certain encryption algorithms or simulating molecular structures. Researchers sometimes discuss how quantum algorithms resemble speed-ups akin to warping time in a computational sense. Extending that metaphor, if actual time manipulation ever entered the picture, it might amplify the quantum speed-up exponentially. Critics point out the potential paradoxes. Wouldn't a time loop for computations risk the typical cause and effect troubles? If the machine sends results back to itself, how does the original question remain unsolved? These puzzles are reminiscent of the grandfather paradox. Nevertheless, theoretical physicists keep exploring the mathematics because it can reveal subtleties about how quantum information flows and how it's constrained by space-time. In reality, we're just beginning to build practical quantum computers without worrying about time loops. They struggle with noise, decoherence, and scalability. But the idea that future breakthroughs might entwine quantum mechanics and space-time geometry is one reason many find this field so exhilarating. It reaffirms that computing isn't just about crunching numbers. It can be a window into the deepest structures of the universe, possibly even challenging our notions of past, present, and future. Inflationary multiverse. There's a blockbuster idea in cosmology that the early universe underwent a rapid expansion called inflation. Right after the Big Bang, space may have ballooned exponentially fast. While that's remarkable on its own, some versions of inflationary theory suggest it might never stop completely, spawning multiple bubble universes in an endless process known as eternal inflation. This collection of bubbles is often referred to as the inflationary multiverse. Picture a pot of boiling water. Each bubble could represent a universe with its own physical laws. forming and expanding while the surrounding water keeps boiling, generating even more bubbles. In some bubbles, conditions might allow life, while in others, the fundamental constants might be so different that stars never form. This scenario tries to explain why our universe seems so well suited for life. Maybe we're just in one bubble among countless others, and ours happens to have the right conditions. Evidence for inflation itself comes from observations of the cosmic microwave background, subtle patterns that fit well with the idea of an ultra-fast early expansion. But proving an actual multiverse is trickier. If other bubbles lie far beyond our cosmic horizon, we can't directly detect them. Critics argue that the inflationary multiverse is more speculation than science, as it might be impossible to test. So, the concept captivates many. It merges astrophysics with quantum mechanics and strings, leading to the idea that the vacuum energy in different bubbles could be different, forming distinct universes. Some see it as an elegant way to explain the otherwise surprising coincidences of cosmological parameters. Others worry it's more of a philosophical stance than a testable theory. Regardless, the inflationary multiverse fosters imaginative thinking. Could infinite versions of reality exist? Does each bubble carry unique cosmic stories, or maybe versions of ourselves leading parallel lives? While these questions can veer into science fiction territory, they also spur new lines of inquiry in physics. Researchers keep pushing the boundaries of observation, hoping to find indirect hints of collisions between bubble universes or other signatures. For now, it stands as a grand vision, illustrating how far we're willing to stretch the cosmic narrative to make sense of the universe we see. Anthropic Principle. There's a principle in cosmology that tries to explain why the universe seems tailor-made for life, the Anthropic Principle. At first glance, it simply states that we observe the universe to be compatible with our existence because, well, we exist. But it has deeper layers. The weak version says that since we're here to ask the question, the universe must have the necessary conditions for our kind of life. The strong version goes further, proposing that the universe must be set up to produce observers at some point. One way to think of it is as a self-selection effect. If you're a fish in a lake, the reason you notice there's always water around is that you couldn't exist in a dry pond. Similarly, we notice physical constants and environmental conditions that allow life because, otherwise, we wouldn't be here to take note. The Anthropic Principle often pairs with the multiverse idea, suggesting that out of countless universes with random variations, we happen to be in one of the rare places that support life. Some find this principle elegant, bridging the gap between improbable cosmic coincidences and our presence. Others see it as a conversation stopper that discourages deeper explanations. Why are fundamental constants like the speed of light or the strength of gravity what they are? The Anthropic Principle replies, they have to be this way, otherwise we wouldn't be here. A light-hearted analogy is a lottery ticket. You might say, of course I won, or else I wouldn't be telling you this story. It explains the event from a survivor's viewpoint, but it doesn't reveal the underlying odds or mechanism that caused the lottery to occur. Philosophically, the Anthropic Principle can venture into tricky territory. Some interpret it as a cosmic design argument. Others see it strictly as a logical constraint on our observations. While it doesn't give direct testable predictions, it does influence how we think about cosmology. It suggests that the unusual precision of certain universal laws might be less shocking if we consider an ensemble of possibilities. Love it or hate it, the Anthropic Principle remains a thought-provoking lens through which to interpret why the universe is so accommodating to life like ours. Van Stockum Dust. There's a lesser-known solution to Einstein's field equations called Van Stockum Dust. It describes an infinitely long, rotating cylinder of dust or fluid. Because it's rotating, it drags space-time around in a twisted manner. reminiscent of how rotating black holes create frame dragging. In this specific setup, some mathematicians and physicists have pointed out that closed time-like curves could arise, meaning the geometry might allow for time loops. A simpler illustration might be a giant rotating spindle of cotton candy, where you swirl sugar around a stick. In the Van Stockum model, there's no stick at the center, just dust in a cylindrical shape spinning on its axis. If you're near the surface of that spinning mass, the swirl could become so extreme that you might find a path in space-time that loops back to your own past. However, Van Stockum Dust is an idealized scenario. An infinite cylinder is hard to conceive in reality. Everything we see in the universe has some finite length or boundary. Yet, these solutions matter because they show what Einstein's equations can do under extreme conditions. They remind us that general relativity can predict strange effects if we allow for unusual mass distributions or geometric setups. Does this mean you can build a time machine by spinning a huge cylinder of dust? Probably not. Real-world attempts to replicate such conditions would face many challenges, and it's unclear if you could maintain the necessary stability or if other physical laws, like quantum mechanics, would intervene. Plus, infinite anything is typically a mathematical convenience rather than an actual possibility. So, Van Stockum Dust stands alongside other exotic solutions, like Gödel's rotating universe, as a demonstration that the geometry of space-time can become quite twisted, potentially opening the door to time travel loops. Whether or not such configurations exist in nature, they expand our sense of what's mathematically possible. In doing so, they highlight the interplay between matter distributions and the structure of space-time, pushing us to keep questioning where the boundaries of physics truly lie. Krasnikov Tube. There's a fascinating geometric construct in relativity called the Krasnikov Tube. It's a speculative space-time shortcut proposed by physicist Sergei Krasnikov. Unlike a wormhole that connects two distant points, a Krasnikov tube is more like a one-directional route that shortens travel time between two locations. The trick is to engineer space-time so that signals, or travelers, can effectively move faster than light would in normal space without locally breaking the speed of light limit. Think of it like building a special highway in the vacuum of space. You prepare the region in advance by traveling at high speed, which sets up the tube's geometry. Then, once it's configured, you can zoom back along the tube faster than light would if it traveled outside of it. It's important to note that from the local perspective, nothing exceeds light speed. It's the overall geometry that does the heavy lifting, letting you beat a signal that takes the usual route. A fun analogy might be if you could build a road on Earth that somehow shortened the distance between two cities so that it's less than what a straight line would be. It sounds impossible in normal geometry, but in curved spacetime, the rules can bend enough to allow such illusions of superluminal travel. As with other exotic spacetime constructs, you'd need negative energy or exotic matter to stabilize a Krasnikov tube. That's the typical requirement for anything that tinkers with the structure of spacetime to create shortcuts. Additionally, the tube might lead to causal paradoxes if combined with other routes, potentially allowing closed time-like curves. So, it's not a free lunch. Messing with space-time geometry can come at the cost of logical headaches. While no one expects to build a Krasnikov tube anytime soon, such theoretical ideas are valuable in that they highlight just how flexible Einstein's equations can be, given the right conditions. They also serve as cautionary tales about the complexities of trying to outsmart the cosmic speed limit. Ultimately, the Krasnikov tube remains a mathematical curiosity that challenges our notions of distance and causality, reminding us that the universe still holds plenty of surprises in its underlying geometry. Exotic particle accelerators. There's ongoing research into new ways to speed up particles without relying on giant circular rings or lengthy linear tunnels. These are sometimes called exotic particle accelerators, and they use innovative methods, like plasma wake fields, laser-driven boosts, or advanced beam technologies, to accelerate particles to high energies over much shorter distances than traditional accelerators. To picture how these might work, consider riding a surfboard on an ocean wave. In a plasma wake field accelerator, scientists shoot a high-energy pulse through a plasma, an ionized gas, creating a wake. Electrons or other particles then surf that wake, gaining huge amounts of energy in a tiny fraction of the space required by conventional accelerators. The hope is to miniaturize accelerators so that you could achieve the same energies as, say, the Large Hadron Collider, but in a machine no bigger than a room or a small building. Other ideas involve ultra-intense lasers. Focused laser beams can create electric fields strong enough to catapult particles forward at incredible speeds. Refined, these methods might lead to tabletop accelerators capable of producing particle beams for medical treatments like cancer therapy or for fundamental physics experiments that currently require massive facilities. One analogy is upgrading from a gentle escalator to a supercharged elevator that rockets you up multiple floors in seconds. Conventional accelerators are huge and expensive, requiring miles of infrastructure. Exotic accelerators promise to deliver that same or greater oomph in a smaller package. They also sometimes promise more precise control over the particle beam, which can be crucial for both research and medical applications. So, these approaches are in development. Engineers face challenges stabilizing the beams, making them high quality, and avoiding disruptions in the plasma or laser fields. But each year sees progress, hinting that future particle accelerators might look radically different. They might be smaller, cheaper, and more widespread, allowing more labs, even hospitals, to have their own powerful beams for research or treatment. It's a vivid example of how creative thinking in physics and engineering can transform giant undertakings into something more portable and potentially more transformative for society. Cosmic strings. Let's dive into the idea of ultra-thin, thread-like defects in the universe's fabric, cosmic strings. These hypothetical objects might span enormous distances across the cosmos, yet be narrower than a proton. Their origin story begins in the early universe. When the universe was just born, it may have undergone rapid phase transitions in which different fields changed their states, similar to water freezing into ice. If these transitions were imperfect, they might have left behind thin seams in space-time. One way to think of cosmic strings is to compare them to cracks that form in ice. As water freezes, stresses lead to narrow fissures. On a cosmic scale, instead of water, you have the newborn universe cooling and settling into distinct energy states. Where the transition didn't go smoothly, you could end up with a cosmic string. Unlike cracks in ice, though, these strings would carry immense energy, so much that a length of string the size of a human hair could outweigh a large mountain. Why do they matter? For one, if cosmic strings exist, they might tug on surrounding matter and light. Passing light rays could be bent, leading to gravitational lensing effects that astronomers might detect. Also, if two cosmic strings crossed, they might pinch off loops that emit gravitational waves. Detecting those waves would confirm these bizarre filaments, giving us a direct glimpse into the universe's earliest moments. Are cosmic strings real? Nobody knows yet. Some theories from particle physics suggest they could exist, while others say they might have decayed or might never have formed at all. So, research continues. Astronomers keep an eye out for the telltale lensing effects, double images of distant objects aligned in strange ways that might indicate a string's gravitational pull. Experiments listening for certain gravitational wave signatures also hold promise. Whether we find them or not, cosmic strings remain a compelling clue about how the universe evolved. They represent the potential scars from cosmic infancy, possibly bridging our knowledge of high-energy physics and cosmology. If confirmed, they would reshape our understanding of how grand structures emerge and provide a real-life example of how fundamental forces can leave permanent, thread-like imprints on the tapestry of space-time. Monopoles. Some theories predict a particle with only one magnetic pole instead of the usual north-south pair enter the magnetic monopole. Typically, magnets come in pairs. If you cut a bar magnet in half, you end up with two smaller magnets, each with its own north and south. True monopoles, by contrast, would act like isolated north or south poles, carrying magnetic charge the same way electrons carry electric charge. One way to illustrate it is to think about splitting an apple. Cut it in half, and you still have an apple in each hand. With magnets, the same principle applies. No matter how many times you slice them, you get smaller dipoles. Monopoles, however, would be more like holding a single half of the fruit with no second half to be found anywhere. Why haven't we seen them? That's the mystery. Several grand unified theories in particle physics predict monopoles should exist and might have formed shortly after the Big Bang. If they did, they might be extremely rare or nearly impossible to detect with current technology. Some older experiments tried searching for them in cosmic rays or in deep underground detectors, hoping that a monopole might pass through and leave a distinct signature. While no smoking gun has appeared yet, the quest continues. Monopoles could help explain why electric charge is quantized in neat units and might tie together electromagnetic forces with the strong and weak nuclear forces. Detecting a monopole would be revolutionary. We'd finally see a magnetic pole in isolation, reshaping textbooks and bridging the gap between Maxwell's equations and quantum theories in a more elegant way. If a monopole were discovered, potential applications are tantalizing but unclear. Some futuristic ideas speculate about harnessing monopoles for advanced technologies like quantum computing or new energy concepts. More realistically, finding even one confirmed monopole would be enough to pop champagne in physics labs worldwide, given its deep theoretical significance. Until then, the search rolls on with improved detectors and clever new approaches. Monopoles remain a reminder that nature can still hide fundamental particles we've never seen, nudging us to stay open-minded about what's out there and keep refining our methods for peering into the unseen corners of the universe. Analog black holes. There's an intriguing approach to studying black hole-like behavior without venturing into deep space. Analog black holes created in labs. Rather than using gravity, scientists use fluid dynamics or other wave phenomena to mimic some properties of event horizons. They might set up a flow of water or a Bose-Einstein condensate so that waves inside it can't escape past a certain boundary, effectively creating a horizon for those waves. Imagine you're rafting on a river. If the current is gentle, you can paddle upstream. But if you move into a powerful waterfall region, there's a point where no matter how hard you paddle, you get swept over. That point acts like the analog of an event horizon, dividing a region from which nothing, no wave, can return. In a lab, researchers exploit this idea to observe phenomena parallel to Hawking radiation. For instance, quantum-like fluctuations in the fluid can produce pairs of particles at the horizon, one trapped and one escaping, mimicking what we think real black holes do with real particles. Why is this so compelling? Because studying actual black holes directly is notoriously difficult. They're far away, extremely massive, and notoriously shy about revealing their interiors. Analog black holes let scientists probe similar physics under controlled conditions. They can measure how waves behave near the horizon and see if they produce radiation in the predicted way. These experiments are more about testing the mathematics and conceptual underpinnings rather than perfectly replicating everything a cosmic black hole does. Skeptics might say it's just a scaled-down fluid toy, not a true black hole. And that's partly correct. Gravitational black holes involve warped space-time. while analogs rely on fluid flows. So, the equations describing wave propagation can be strikingly similar. If those equations hold up in the lab, it boosts confidence that the same effects apply in the astrophysical setting. Analog black holes highlight a creative side of physics, using tabletop, or at least lab-sized, experiments to shine light on cosmic mysteries. They bridge the gap between abstract theory and tangible observation, suggesting that even the most extreme phenomena in the universe might have parallels in everyday substances, provided we set them up just right and look closely at the waves inside. Negative temperature systems. There's a notion in thermodynamics that temperature can dip below absolute zero. Enter negative temperature systems. This might sound impossible since we learned that 0 Kelvin is the lowest temperature you can reach. But negative temperatures appear in certain physics contexts not because things are colder than cold, but because the definition of temperature in these systems flips. Typically, temperature measures how energy spreads among particles. At higher temperatures, particles have more energy states available. Absolute zero means minimal energy. Negative temperature states, however, pop up in situations where adding energy decreases the total number of accessible states. That's almost like saying your system is so full of energy that there's nowhere else for the new energy to go in the conventional sense. One way to illustrate it is with a population of atoms in different energy levels. If you manage to get most atoms into high energy states and only a few in low energy states, which can happen in specific quantum systems or via laser manipulation, you can create a distribution that resembles a negative temperature. It's more about how the mathematics of energy distribution works than about feeling physically colder than 0 Kelvin. What does this mean in practical terms? These negative temperature systems can behave in odd ways. They might respond differently to pressure changes or display inverted thermodynamic properties. Researchers find them interesting for exploring fundamental principles of statistical mechanics. Sometimes they also appear in magnetic systems or spin ensembles, offering potential pathways for exotic states of matter. It's important to note that you can't combine a negative temperature system with a positive one and make a perpetual motion machine. That would violate conservation laws. The negative temperature concept is more subtle than simply hooking up a below 0 Kelvin entity to a normal system and extracting infinite energy. So, negative temperature states remind us how flexible and counterintuitive quantum or statistical systems can be. They hint that temperature isn't just a measure on a single scale from cold to hot. Under the right circumstances, it can become a tool for describing distributions of energy that defy everyday expectations. It's another sign that the more we delve into the quantum world, the more it shakes up our classical assumptions about what's possible. Firewalls. There's a provocative idea about black holes that at the event horizon, where we once imagined everything passes smoothly, a blazing wall of energy called a firewall might exist. Traditional physics said someone crossing the horizon wouldn't feel anything special at that boundary, thanks to the principle of equivalence in general relativity. But quantum considerations, particularly regarding information loss, have led some to propose that the horizon could be a high-energy zone that incinerates anything trying to pass. One way to grasp the puzzle is to consider the black hole information paradox. If quantum information can't be destroyed, then how do black holes manage to keep it all, especially when they evaporate via Hawking radiation? Some calculations suggest that maintaining the quantum consistency might necessitate an energetic barrier at the horizon, the firewall. That barrier, in theory, would store or process the information somehow, preventing a contradiction. An analogy might be a computer system where sensitive data is quarantined behind a secure firewall to protect it from tampering. If you approach that firewall, it vigorously defends its data. Here, meaning any falling matter might get blasted by intense radiation. This stands in stark contrast to the no-drama scenario, where you'd float through the horizon without noticing anything special at first. Most physicists haven't reached consensus on whether firewalls are real. Many suspect that a complete theory of quantum gravity might resolve the paradox in a different way. Firewalls, while stirring up lively debate, might be a simplified or extreme depiction of what truly happens at the horizon. Others argue we can't just ignore the firewall hypothesis. It's a mathematically consistent solution to the paradox, so it deserves serious attention. While no one has a direct test for black hole horizons at this detail level, the discussion pushes researchers to refine their theories about how space-time, gravity, and quantum fields interact. Firewalls represent a deep tension between relativity, smooth horizons, and quantum mechanics, strict information rules. Whether they exist or not, they underscore that black holes may hold more surprises than we initially believed, pushing us closer to the day we unify gravity with the quantum world in one cohesive framework. Holographic Principle. There's a radical notion in theoretical physics that our three-dimensional universe might be describable by information encoded on a two-dimensional surface, a concept called the holographic principle. It draws its name from holograms, where a 2D film can encode a 3D image. The idea goes further. The entire content of a region in space could be represented on a lower dimensional boundary, suggesting reality might be projected from that boundary. To simplify, consider how a flat computer screen can display a 3D video game world. The genuine 3D depth is an illusion created by projecting information onto a 2D display. With the holographic principle, space and maybe even gravity itself could emerge from quantum information stored on this boundary, typically envisioned at the very edge of the cosmos or around black holes. Physicists Gerard T. Hooft and Leonard Susskind were among those who popularized this principle, partly inspired by black hole thermodynamics. Studies showed that the entropy, or information content, of a black hole scales with the area of its event horizon, not its volume, which was counterintuitive. The holographic principle generalizes that insight to all of space-time, hinting that volume might be an emergent concept rather than fundamental. It's worth clarifying that you don't literally see the world as a 2D movie. Our experience is still very much three-dimensional. But mathematically, the fundamental description might be simpler on a boundary surface, with the extra dimension manifesting as a kind of projection or emergent phenomenon. String theory's ADS/CFT correspondence is a prominent example, relating a gravity theory in a bulk space to a quantum field theory on its boundary. While the holographic principle remains a lively research topic, it has yet to be fully proven or applied to our real universe. Much of the detailed work involves hypothetical spaces with negative curvature, anti-de Sitter spaces. Not quite our universe's geometry. So, it's a beacon suggesting that geometry and gravity could be consequences of a deeper, lower-dimensional quantum reality. If proven correct, it would revolutionize how we see space and the fundamental nature of existence, challenging us to envision that everything we do might be written on a cosmic screen in a more profound way than we ever imagined. Quantum brain theory. There's a perspective that human consciousness might rely on quantum effects in the brain, a broad idea often labeled quantum brain theory. Traditional neuroscience explains thought processes using classical physics. Neurons fire, chemicals diffuse, and signals pass along synapses. But some researchers wonder if the brain's complexity and the phenomenon of consciousness might tap into quantum coherence or entanglement at the microscopic level. A loose analogy is comparing a standard computer to a quantum computer. Standard computers use bits that are clearly 0 or 1, while quantum computers use qubits that can be in multiple states simultaneously, enabling powerful new forms of calculation. Could the brain similarly exploit quantum superposition or entanglement to manage cognition beyond classical means? Penrose and Hameroff, for example, propose orchestrated objective reduction, orchestra, or suggesting quantum processes in microtubules within neurons might contribute to consciousness. Critics argue that the warm, wet environment of the brain is too noisy for delicate quantum states to last long. Quantum coherence typically needs low temperatures and isolation from the environment, conditions not found in the constantly active brain. Yet, quantum biology has uncovered quantum effects in photosynthesis, bird navigation, and other biological processes. It's conceivable that evolution found ways to harness quantum phenomena more than we realize. However, proving quantum processes underlie consciousness is tough. Experiments would require extremely sensitive measurements to catch entanglement or superposition in real-time brain activity, something we're far from achieving. Nonetheless, the question itself sparks debate about whether classical physics is sufficient to explain something as mysterious as consciousness. Even if quantum events do occur in brains, do they meaningfully contribute to thought and awareness, or are they incidental? Some suspect a full explanation might still rest on emergent classical properties of neural networks, leaving little room for quantum magic. Others remain open to the possibility that quantum effects might be the missing piece in understanding subjective experience. As it stands, quantum brain theory embodies the intersection of two great mysteries, the nature of mind and the nature of quantum mechanics. Whether it pans out or not, it offers a fertile ground for fresh experiments and interdisciplinary thinking, pushing us to question the boundaries of both neuroscience and quantum physics. Vacuum metamaterials. There's a futuristic concept about manipulating the vacuum of space itself so it behaves like a material with custom properties. These are called vacuum metamaterials. Typically, a metamaterial is an engineered structure that bends waves, like light or sound, in unusual ways. For example, you might create an invisibility cloak by designing a material that guides light around an object. Vacuum metamaterials take that idea a step further by proposing we can tweak the quantum vacuum to achieve exotic effects. One way to think about it is how a lens focuses light. We shape glass or plastic to direct photons. So instead, we could mold the vacuum structure. We'd bypass the need for bulky lenses. Some theories suggest that by using intense electromagnetic fields, special geometries, or certain arrangements of matter, we might modify the local vacuum so that light or other particles behave differently, even bending in directions that normal space wouldn't allow. It might sound like science fiction, but smaller-scale analogs exist. The Casimir Effect, for instance, shows that placing conducting plates close together changes the quantum vacuum between them, generating a measurable force. That's a sign the vacuum isn't just empty but has properties we can manipulate, albeit in a limited way. Extending such control to create large-scale, vacuum metamaterials is far more speculative. We'd need advanced technologies to maintain configurations that cause desired changes. Potential applications are broad. Advanced lenses for high-energy physics experiments, new forms of propulsion that exploit vacuum forces, or innovative ways to route electromagnetic signals. Some even dream about warping or engineering space-time for advanced transportation. But these remain in the realm of radical theorizing. Achieving macroscopic control over the quantum vacuum seems beyond our current grasp, requiring leaps in energy, precision, and understanding. Nevertheless, vacuum metamaterials showcase how an empty vacuum is anything but simple in quantum physics. There's a dynamic field with virtual particles popping in and out, capable of being shaped, at least in principle, into exotic states. If technology progresses, maybe we'll discover that the vacuum can be sculpted into forms that revolutionize optics, electronics, or even space travel. Until then, it's a mind-expanding concept hinting at how much potential still lies untapped in what we used to call nothingness. Magnetars as energy sources. There's an extreme type of neutron star known as a magnetar, famed for sporting magnetic fields billions of times stronger than anything we can replicate on Earth. Imagine a city-sized stellar remnant spinning wildly, with a magnetic field so intense it could rip apart atoms if you got too close. These objects occasionally let loose bursts of X-rays and gamma rays that can outshine entire galaxies for brief moments. Why consider them for energy sources? Because that immense magnetic field holds incredible potential. If a civilization could harness just a fraction of a magnetar's power, it might fuel everything from starships to planet-wide energy grids. An analogy might be trying to tap into a raging tornado. If you could convert the tornado's kinetic energy safely, you'd have a massive power supply. The challenge, of course, is not getting shredded in the process. Harnessing magnetar energy wouldn't be straightforward. Even approaching one is perilous. Its field could scramble electronic equipment and tear apart molecules at close range. The environment is drenched in high-energy radiation, deadly to life as we know it. The engineering needed to set up an energy harvesting station near a magnetar is mind-boggling. You'd need advanced shielding, robust materials, and ways to transport the harvested energy across potentially vast interstellar distances. So, some sci-fi scenarios imagine building a structure, a Dyson-like sphere or a swarm of collectors, around a magnetar, capturing the intense electromagnetic output. Alternatively, advanced field propulsion could channel magnetic field lines to accelerate a spacecraft. It's all highly speculative but underscores how magnetars represent a cosmic powerhouse that dwarfs our usual energy sources. From an observational standpoint, magnetars also shed light on how matter and energy behave under extreme conditions, teaching us about fundamental physics beyond typical laboratory capabilities. Even if we never harness them for practical power, studying magnetars helps us refine theories about neutron stars, quantum electrodynamics, and the life cycles of massive stars. In essence, magnetars are nature's ultra-high voltage dynamos. They serve as a tantalizing reminder that if technological civilizations persist long enough, they might explore or even exploit bizarre cosmic objects for energy, pushing the boundaries of what's possible in a universe teeming with extremes. Planck Star. There's a speculative idea that when matter collapses into a black hole, it might eventually rebound as something called a Planck Star. Normally, we think of black holes as points where everything vanishes into a singularity. But in loop quantum gravity and related theories, space-time could be quantized, preventing a true singularity from forming. Instead, matter gets compressed to a point of maximum density around the Planck scale and then bounces back, releasing energy in a colossal burst. Think of a spring. Push it down, and it resists more and more until it can't be compressed further. Then it snaps back. The Planck Star scenario suggests a similar process might happen inside a black hole on extremely long timescales. Eventually, the star re-expands, releasing whatever was swallowed. This could resolve the information paradox. The quantum information that fell in doesn't vanish but emerges after a potentially immense delay. No one has observed a Planck Star directly, and the times involved might be longer than the age of the universe for large black holes. But if smaller black holes exist, they might transition to Planck stars faster, emitting characteristic radiation. In principle, advanced astronomy instruments could pick up hints if we know what to look for. Some see Planck stars as an alternative explanation for phenomena like gamma-ray bursts or fast radio bursts. If one of these transitions occurs, it might pour out a flood of high-energy particles. It's speculative, but it emphasizes that black holes might not be the final, forever prisons we initially thought. If quantum gravity has a say, regardless, Planck stars highlight how incomplete our knowledge is about what happens at extreme densities. General relativity alone predicts a singularity, But quantum mechanics warns that singularities might be unphysical. Loop quantum gravity is one proposed fix, turning the singularity into a bounce. Whether Planck stars truly exist or are just a mathematical artifact remains uncertain. So, the concept pushes us to seek a unified theory that explains how matter and quantum effects interplay at their most intense, where the universe's secrets may be hiding, awaiting our next big breakthrough. Time crystals. There's a remarkable idea about matter that repeats in time the way ordinary crystals repeat in space. Those are time crystals. Typically, a crystal has a lattice structure that repeats in all spatial directions, like the orderly array of atoms in salt. The time crystal goes further, arranging itself in a repeating pattern over time. In other words, part of the system cycles back and forth without using energy in the usual sense. This concept was proposed by Frank Wilczek, a Nobel laureate, and initially met with skepticism. Then, experiments showed certain quantum systems could indeed exhibit time crystal behavior. For instance, a set of spins or atoms, driven by lasers or microwaves, can settle into a stable oscillation that never fades. It's not perpetual motion in the classic sense, because the entire setup includes a drive or environment that keeps the cycle going, but the system's own internal energy doesn't keep changing net. To draw a parallel, imagine a child's top spinning on the floor. Normally, friction slows it down. But if there was a special trick that let it spin forever at a constant energy, that might look like a time crystal phenomenon. In practice, time crystals rely on quantum effects and the concept of symmetry breaking in time. Why is this interesting? Because it challenges the usual thermodynamic picture. We expect systems in their lowest energy state to be static, not oscillating. Time crystals show you can have a ground state that nonetheless exhibits periodic motion. Researchers see potential uses in quantum computing, where stable, repeating states might store information or maintain coherence. Creating a time crystal isn't about everyday material spontaneously hopping on a cosmic treadmill. Instead, you need very specific conditions, ultra-cold atoms, carefully tuned laser fields, or other precise setups. But once formed, these systems can keep ticking on their own schedule, reminiscent of a clock that never fully winds down. Time crystals remind us that even the concept of equilibrium can become richer in quantum physics, opening doors to new phases of matter. They offer a glimpse into how subtle symmetries can manifest in ways we never imagined, hinting that the universe's capacity for hidden order runs even deeper than we might suspect. Superfluid vacuum theory. There's a viewpoint where the vacuum of space isn't truly empty but behaves like a superfluid, a fluid with zero viscosity, on a cosmic scale. Proponents of superfluid vacuum theory, SVT, suggest that particles and fields move through this fluid, and phenomena like gravity emerge from its properties. In this picture, space-time itself acts more like a medium than a static backdrop. A simplified analogy is imagining Earth's atmosphere. Planes move through it, sometimes facing drag, sometimes aided by wind currents. Now tweak that analogy so the wind is nearly frictionless, like a superfluid. If the vacuum is a superfluid, then changes in pressure or density might correspond to gravitational effects or variations in how particles travel. The classical vacuum, which we've always deemed an absence of matter, becomes a dynamic substance. SVT tries to tackle quantum gravity by treating space-time less as a purely geometric entity and more as a fluid governed by quantum rules. If this were correct, things like black holes might be vortices in the superfluid, and the universal expansion might be akin to changing fluid density. At small scales, wave-like excitations in this superfluid might show up as fundamental particles. Critics question whether SVT can match all known observations as precisely as general relativity and the Standard Model. After all, we have a lot of experimental data that must be explained. So, some see it as an interesting route because it resonates with how superfluid helium can exhibit bizarre properties, like frictionless flow or quantum vortices. If the vacuum is similarly exotic, maybe gravity is an emergent effect of that underlying fluid rather than a fundamental force. While no definitive tests confirm or disprove SVT outright, bits and pieces might be gleaned from high-precision cosmological observations or particle physics experiments. If anomalies appear that standard theories can't easily explain, superfluid vacuum models might come into play. Regardless, it underscores that we're still far from a consensus on how space-time and quantum fields intertwine. Exploring creative frameworks like SVT stretches our imagination and may guide us toward fresh insights on the true nature of the vacuum, one of the biggest somethings hidden in what we call nothing. Probability bubbles. Consider the idea of manipulating probability itself at quantum scales to create probability bubbles, regions where certain events become more likely or less likely than usual. In standard quantum mechanics, outcomes are governed by wave functions that give probability distributions. You measure a particle's position, and you get a result consistent with those probabilities. But some futurists and theorists speculate, what if we could alter the odds, shaping local quantum realities? It's akin to rigging the shuffle of a deck of cards so that aces pop up more frequently, except this time the deck is the fabric of quantum possibilities. The concept of probability bubbles usually emerges in discussions about advanced technologies or exotic physics where you manipulate the wave function environment to favor certain outcomes. For instance, maybe you'd want a bubble where nuclear fusion events happen more readily at lower temperatures, or a bubble where chemical reactions become more probable, enabling new forms of energy or manufacturing. Critically, this remains a thought experiment rather than established science. There's no known mechanism to systematically skew quantum outcomes on demand beyond typical quantum interference or measurement choices. If anything, quantum mechanics is quite strict about preserving overall probabilities. But brainstorming about probability bubbles pushes us to consider how chance might not be as fixed if we could control the boundary conditions or the environment in radical ways. One imaginative analogy is wearing special quantum glasses that let you see the wave function around you and tweak the areas that look densest. In reality, wave functions are not so easily manipulated without measurement or interaction, which collapses or changes them in complex ways. Any large-scale attempt to shape probability might destroy the very coherence needed to do so. So, the notion resonates with deeper philosophical questions. Could advanced civilizations or future experiments harness quantum weirdness to tilt the odds, effectively engineering reality at a fundamental level? Even if it's purely speculative, it highlights the interplay between randomness and control in quantum physics, reminding us that the line between possible and impossible can blur when we venture deep into the quantum domain. Hyperdimensional travel. Some scenarios propose we can bypass long distances by stepping into extra dimensions, an idea commonly called hyperdimensional travel. Standard physics sees our universe as having 3 spatial dimensions plus 1 of time, but string theory and other advanced models propose more dimensions that may be hidden or curled up at tiny scales. If these higher dimensions exist, maybe we can exploit them to take shortcuts. Picture it as folding a piece of paper to bring 2 distant points together. In our familiar 3D space, that's just an analogy. But if higher dimensions were accessible, you might do something like that for real. Step into a higher corridor, move a short distance there, then pop back out somewhere far away in normal space. It's reminiscent of sci-fi hyperspace jumps, only with a theoretical basis in certain brain world or higher dimensional models. The challenge is that these extra dimensions, if they're out there, appear to be extremely small or otherwise hidden, so it's not clear how we'd fit a spaceship or even a single atom through them. Engineering such a leap would require energies or manipulations of space-time far beyond anything we've achieved. Alternatively, a civilization advanced enough might expand or unfold these compact dimensions temporarily, creating a passage. Though it sounds purely fictional, theoretical physicists sometimes toy with brane world ideas. Maybe our 3D universe is a brane in a higher dimensional bulk. They investigate how gravity might leak into or out of these extra dimensions, or how exotic phenomena could hint at higher dimensional interactions. If we detected anomalies in gravitational behavior at small scales, it might hint that these hidden dimensions are real. Of course, turning that into practical hyperdimensional travel is another story, arguably more distant than warp drives or wormholes. But the concept stirs our imagination. There could be entire directions in reality we can't perceive, yet if we found a way to access them, it would redefine exploration and technology. For now, hyperdimensional travel remains a captivating backdrop for theoretical work and speculative fiction, a reminder that the universe may be bigger and stranger than what our 3 familiar dimensions show us. In theory, there's a unifying framework in string theory known as M-theory, which proposes that all the different string theories are just various aspects of a single underlying theory that includes membranes, extra dimensions, and a host of exotic possibilities. Originally, string theory split into 5 different versions, each with subtle differences in how strings vibrate and how supersymmetry is realized. M-theory aims to tie them all together into one consistent picture, where E is often said to stand for membrane, mother, or even mystery. One way to simplify it is to think about different video games that share the same engine but appear quite different on the surface. Underneath, they're all built on the same fundamental code. M-theory suggests that behind the varied formulations of string theory, there's a single engine or framework. It typically works in 11 dimensions, 10 spatial plus 1 of time. In some scenarios, the fundamental objects aren't just 1D strings but also 2D membranes and higher dimensional branes. Why does it matter? Physicists hope M-theory could reconcile quantum mechanics with gravity, providing a quantum gravity theory that also unifies the other fundamental forces. This has been a holy grail in physics for decades. If successful, it might explain everything from the structure of space and time to how particles get their masses, and even the nature of dark matter or dark energy. Critics note that M-theory remains largely unproven and very abstract. We don't have direct experimental evidence for extra dimensions or the strings and branes. Moreover, the landscape of possible solutions within M-theory is vast, making it hard to pinpoint which version, if any, describes our universe. Nonetheless, many theorists see it as our best mathematical candidate for unification, with properties that elegantly weave together advanced mathematics and fundamental physics. M-theory also touches on cosmology, offering scenarios where universes bubble off in higher dimensional space or where cosmic inflation ties to brane collisions. Whether it truly captures nature's blueprint or stands as a grand but untestable theory remains a topic of spirited debate. So, the quest for M-theory exemplifies the human drive to find a single explanatory tapestry for all forces and particles, reminding us that the deepest truths about our universe might be hidden within higher dimensions and vibrating membranes we've yet to directly perceive. Brane Cosmology. Picture the entire universe as a membrane, or brane for short, floating in a higher dimensional sea. That's the central idea behind Brane Cosmology, a branch of string theory where our familiar 3D world is just one slice of a bigger, multidimensional bulk. In this scenario, all the matter and forces we see might be confined to our brain, while gravity can leak out into extra dimensions. To get a grasp on it, imagine a flat sheet of paper representing our universe, with everything we know, stars, galaxies, you and me, stuck on that sheet. Now think of a large room that holds many such sheets, each one potentially hosting its own universe. If gravity is able to flow among sheets, you might occasionally sense the presence of another brane without being able to directly see it. This leads to speculation that parallel universes could be physically near us, just separated by an extra dimension. Brane Cosmology offers an intriguing angle on major cosmic puzzles. For instance, the acceleration of our universe's expansion might be influenced by interactions with other branes. Some versions even suggest the Big Bang started as a collision between two branes, releasing the energy that formed all matter in our universe. It's a startling twist on traditional inflationary models, aiming to tie quantum theory and gravity together. Critics note that while Brane Cosmology is mathematically rich, it's tough to test experimentally. Detecting extra dimensions, if they exist, would require energies beyond what we can easily achieve, or we'd need to catch subtle anomalies in gravitational measurements. So, physicists keep an eye out for hints. If gravity behaves unexpectedly at tiny distances, it might hint that it's leaking into those higher dimensions. Whether Brane Cosmology ends up as the correct blueprint or not, it extends our imagination of what universe truly means. By pushing beyond a 3D horizon, it nudges us to see that everything we experience might be just one piece of a more grand and layered reality. In that sense, it's a bold attempt to answer age-old questions about our origins and ultimate place in the cosmos, all while challenging our instincts about space itself. Quantum foam. Picture space at its smallest scale, trillions of times tinier than an atom, bubbling and boiling like foam on ocean waves. That wild mental image is what physicists call quantum foam. At these minuscule lengths, known as the Planck scale, the usual notions of smooth space-time break down. Instead, quantum fluctuations might create a frothy, ever-shifting structure where distances and even time intervals fluctuate constantly. Imagine looking at a calm sea from far away. It seems flat, but up close, waves and bubbles churn in a frenzy. The same goes for space-time. At everyday scales, it appears smooth and continuous. Zoom in enough, though, and quantum effects could make it roil with random bursts of energy. The foam concept arises when we try merging general relativity, which sees gravity as smooth curvature, with quantum mechanics, which is all about discrete probabilities and vibrations. Why does this matter? Because if space-time truly foams at tiny scales, it might explain phenomena we can't fully account for yet, like the energy content of empty space or the behavior of gravity at very high energies. Quantum foam could also be the realm where wormholes spontaneously flicker in and out of existence on subatomic scales. While such fleeting wormholes are too small and short-lived to pass through, they highlight how bizarre reality might be down there. Observing quantum foam directly is nearly impossible with current technology. We'd need instruments capable of peering at distances around the Planck length, about 10 to the power of -35 meters, which is far beyond our reach. So, researchers look for indirect clues. Some theories predict slight delays in how photons of different energies travel through foam-like space, possibly detectable by advanced telescopes watching distant gamma-ray bursts. Whether quantum foam will remain a metaphor or become a concrete part of physics remains to be seen. It's a reminder that our everyday view of space, like the surface of a tranquil ocean, could be hiding chaotic undercurrents. As we refine our theories of quantum gravity, we may find that at the smallest possible scale, space is alive with quantum jitter, challenging our intuition about what empty truly means. Vacuum collapse. Ever worried the universe might be on borrowed time? There's a theory called vacuum collapse that suggests our universe's vacuum isn't truly in the most stable state. Instead, we might inhabit a false vacuum, like a ball resting in a shallow dent rather than the deepest trough. If a quantum fluctuation or high-energy event triggers the vacuum to fall into a lower energy state, a bubble of true vacuum could expand at nearly the speed of light, annihilating everything in its path. Think of a pane of glass that's under stress. It seems stable until a small crack forms. Then it shatters quickly. Similarly, if a tiny region somewhere in the cosmos spontaneously transitions to a more stable vacuum, that region would expand, rewriting the laws of physics inside the bubble. Particles, forces, and fundamental constants could all change dramatically, making our familiar chemistry impossible. Essentially, it's game over for life as we know it. Should we panic? Probably not anytime soon. If vacuum collapse is possible, it might require extraordinary conditions, energies we don't typically see except near the Big Bang or around the most extreme cosmic processes. Also, the lifetime of a false vacuum could be immense, far surpassing the current age of the universe. We might just get lucky with how things shaped up after the Big Bang. Scientists started considering this idea when they learned about spontaneous symmetry breaking in field theories and how certain potential energy landscapes can have local minima that look stable but aren't the absolute lowest point. Observational data about the Higgs boson and other particles feed into these calculations. Some suggest the parameters of our standard model might put us near a metastable boundary, though this is still debated. Despite sounding scary, vacuum collapse highlights how our universe's very fabric could hinge on delicate balances. It makes us reflect on the possibility that the familiar physics around us might just be one choice among many, and that cosmic change can be as catastrophic as flipping a cosmic switch. For now, the best we can do is keep studying particle physics and cosmology, hoping to pin down whether the vacuum we inhabit is truly stable or just temporarily complacent. Sakharov's induced gravity. Imagine gravity not as a fundamental force, but as something that arises from the collective behavior of quantum fields. That's the essence of Sakharov's induced gravity, a concept introduced by the Russian physicist Andrei Sakharov. Instead of starting with the idea that space-time bends due to mass, Sakharov proposed that space-time curvature might emerge if you look at how quantum fields interact at very short distances. A helpful analogy comes from everyday life. Water in a bucket doesn't fundamentally force you to swirl it around, but the friction and interactions within the fluid can create patterns or vortices that look like emergent phenomena. In Sakharov's view, the vacuum is like a sea of quantum fields. When these fields fluctuate, they might produce effects that mimic a gravitational field. In other words, mass and energy might cause changes in the underlying quantum fields, effectively bending space without gravity being a standalone entity. Why is this appealing? Because unifying gravity with quantum mechanics is one of physics' biggest challenges. If gravity is induced from underlying quantum processes, that might help us blend Einstein's equations with the quantum realm more elegantly. Sakharov's idea also suggests that general relativity's parameters, like Newton's gravitational constant, might be determined by the properties of these quantum fluctuations, opening a pathway to explain why they have the values we measure. Critics point out that turning gravity into a derived effect is tricky, and many attempts to flesh out Sakharov's proposal run into technical snags. We still don't have a final, induced gravity model that matches all observed data. Nonetheless, it continues to inspire research as it flips the script. Rather than forcing gravity into the quantum mold, you coax it out of quantum fields in a more natural way. Sakharov's approach underscores the bigger theme that empty space is never truly empty. The vacuum throbs with quantum activity, and from those activities, phenomena we label fundamental, like gravity, might emerge, even if the final theory doesn't exactly follow Sakharov's blueprint. Exploring these ideas helps us see gravity in a fresh light, inching us closer to the ultimate dream of a seamless union between general relativity and quantum physics. Unruh Effect. Picture yourself in a rocket, accelerating through empty space. Classical physics says you'd see a vacuum outside. No particles, just emptiness. But quantum field theory offers a twist. If you accelerate, you might detect a warm glow of particles known as Unruh radiation. This phenomenon, predicted by physicist Bill Unruh, suggests that the concept of a vacuum is observer-dependent. While someone coasting at constant speed sees nothing, the person accelerating senses a bath of particles, as though space were heated. A simpler analogy is riding in a car on a cold day. When you're still, you don't feel much air on your face. But if you roll down the window and speed up, that rush of air stings like it's colder, even though the outside temperature is the same. In quantum terms, your accelerating frame shifts how you perceive the underlying quantum fields, making them appear to have thermal energy. This effect is related to Hawking radiation at black hole horizons. Observers far from the black hole see particles emitted, but someone freely falling in might not notice anything special at the horizon. In both cases, the key insight is that acceleration and gravity can change what's considered a vacuum. The Unruh temperature is usually tiny for human-scale accelerations. You'd need extreme accelerations, far beyond what we experience in daily life, to detect any real heat. That makes it nearly impossible to confirm in straightforward lab tests, although people have proposed experimental setups involving intense lasers or fields to approximate the effect. Despite the challenges, the Unruh effect remains important theoretically because it supports the idea that particle content depends on an observer's motion. It's one more sign that quantum physics and relativity, when merged, yield results that defy common sense. Some even speculate about harnessing Unruh radiation for exotic propulsion or energy, though that remains purely speculative. In essence, the Unruh effect reminds us that emptiness is never absolute. If you change your perspective, literally by accelerating, what was once nothing can become something, a tangible glow of particles. It's another remarkable piece of the puzzle bridging quantum field theory and general relativity, hinting that how we move through space-time can transform our understanding of the vacuum itself. Femtosecond laser fields. Imagine firing a laser pulse so short it lasts just a few quadrillionths of a second. These are femtosecond laser fields, ultra-brief bursts of intense light that pack enormous peak power. Over the past few decades, scientists have refined the technology to create and harness these fleeting flashes. The result? Tools that can slice through materials with surgical precision, explore fundamental processes in chemistry, and even simulate extreme astrophysical conditions in a lab. To put it in perspective, a femtosecond is to a second what a second is to about 31.7 million years. It's an incredibly tiny slice of time, allowing researchers to freeze-frame events at the molecular or even electronic level. Picture stopping a hummingbird's wings mid-flap or pausing raindrops in midair. Only now, you're capturing electron jumps in atoms or the formation and breaking of chemical bonds. How does this help? For one, femtosecond lasers make it possible to do pump probe experiments. You use one pulse, the pump, to excite a system, like kicking an electron out of place, then use another, the probe, to see what happens over time. By adjusting the delay between pulses, you build a movie of ultra-fast phenomena. This technique revolutionized our understanding of reaction dynamics and has practical applications in designing new materials or optimizing industrial processes. Moreover, when you focus these lasers onto a tiny spot, the electric field can become so intense it rivals the field strength inside stars. That means you can probe high-energy physics in a tabletop setting. Some labs generate plasmas that mimic conditions in stellar cores, giving insights into fusion or exotic states of matter. Others use femtosecond pulses to create high-speed laser-driven accelerators, potentially shrinking particle accelerators. Additionally, surgeons have found uses in precise eye procedures. Femtosecond lasers can reshape corneas or cut tissue with minimal damage to surrounding cells. It's the same principle of delivering an enormous burst of energy so quickly that there's little time for heat to spread. In short, femtosecond laser fields exemplify how pushing the boundary of time resolution can unlock extraordinary control over matter and energy. They serve as a powerful reminder that even incredibly small intervals in time can hold the key to big breakthroughs in both basic science and practical technology. Causality violations. Ever wondered if events could happen out of order? That's the heart of causality violations, the notion that cause and effect might not always line up in a neat forward sequence. In physics, we normally assume that if a cause is B, then A must come before B. But certain theoretical constructs, like closed time-like curves or exotic space-time geometries, suggest it could be possible, at least mathematically, to encounter situations where effect precedes cause. A quirky analogy might be sending yourself a letter from the future. If you could drop a note into a time loop, telling your past self to avoid some mistake, you'd be the effect creating its own cause. It's a mind-bending paradox that calls into question how logical consistency holds together. Scientists refer to chronology protection as the idea that physics might have built-in safeguards preventing actual paradoxes from happening, possibly via quantum effects that disrupt such loops. Why do we even consider such ideas? General relativity, Einstein's masterpiece, allows solutions where space-time curves back onto itself in time. If you're traveling through one of these loops, you might arrive at a point in your own past. While these solutions are often dismissed as non-physical, they're not outright forbidden by the equations. Then there are quantum theories suggesting retrocausality, where future measurements could influence the past in subtle ways. Although these remain fringe, they keep the conversation about causality open-ended. From a practical standpoint, we don't see violations of cause and effect in everyday life. Entropy generally increases, memories form in one direction, and we can't just rewrite history. That's why most physicists believe real-world causality violations either don't happen or are prevented by deeper laws we haven't fully articulated. So, the possibility that causality might break down in extreme regimes, like near rotating black holes or in early universe conditions, fuels theoretical research. Even if we never see a time travel loop, exploring these scenarios clarifies the assumptions that keep our reality in order. It's one more way that delving into the edges of physics forces us to question bedrock principles, like the unbreakable sequence of cause leading to effect. Artificial mini-Big Bangs. Imagine recreating the fury of the universe's birth in a lab on a vastly smaller scale. Of course, that's what scientists aim for when they collide particles at near-light speed in powerful accelerators, producing conditions so hot and dense they resemble the early moments after the Big Bang. While we can't replicate the entire cosmic event, these mini-Big Bangs let us probe the intense physics that dominated when the universe was less than a second old. Picture two speeding bullets slamming into each other, only these bullets are heavy atomic nuclei. In facilities like the Large Hadron Collider, LHC, or RHIC, Relativistic Heavy Ion Collider, gold or lead ions smash together at tremendous energies, momentarily creating a fireball of quarks and gluons, the fundamental building blocks of matter. This fireball cools in a fraction of a second, but while it's hot, it forms a special state called a quark-gluon plasma. That's the same soup that filled the young universe before protons and neutrons existed. Scientists sift through the debris to study how quarks behave when freed from their usual confinement. They look for patterns in the showers of particles produced, searching for new insights into the strong nuclear force that binds quarks together. Sometimes, exotic states or rare collisions might hint at physics beyond the standard model. Mini Big Bang experiments also help refine our knowledge of how matter formed in the early cosmos, bridging the gap between theory and observation. It's not without controversy. Some feared that creating such energies might spawn microscopic black holes or strangelets that could threaten Earth. But extensive calculations and experiments have put those concerns to rest. Nature itself bombards us with cosmic rays at higher energies all the time. And we're still here. So, the idea that we can spark tiny versions of cosmic creation in a collider is both thrilling and humbling. It underscores how far technology has come, allowing us to glimpse the universe's infancy in a controlled setting. Each new round of data brings us closer to understanding not just the building blocks of matter, but the very moment our cosmic story began, a time when everything around us was once a single hot, dense spot. Quantum tunneling travel. Envision walking through a wall without breaking it down. That's the essence of quantum tunneling, a phenomenon where a particle can breach an energy barrier seemingly too high to cross. While it's a standard effect in quantum mechanics at atomic scales, people sometimes wonder if it could enable macroscopic travel. Could we someday tunnel entire spacecraft through obstacles or even across vast cosmic distances? In regular life, obstacles stop you if you lack the energy to move them. But quantum objects have wave-like properties, meaning there's a small probability they'll appear on the other side of a barrier, even if they don't have enough energy to climb over it in the classical sense. It's a bit like water in a bucket spontaneously splashing to the other side of a wall. Though that's a loose analogy, this effect is crucial for nuclear fusion in stars. Protons fuse because they occasionally tunnel past their mutual repulsion. It also underpins modern technology, like tunneling diodes and scanning tunneling microscopes. When we scale up from subatomic particles to everyday objects, though, quantum tunneling becomes astronomically improbable. The chance of all your body's atoms simultaneously tunneling through a door at once is so tiny that it may never happen in the age of the universe. Even so, speculative theories discuss whether advanced civilizations or future technologies might manipulate quantum states so effectively that they could induce a kind of controlled tunneling for larger systems. Some tie it to ideas about probability bubbles or artificially shaping wave functions. But we're far from turning that into real engineering. The power requirements and precision would be off the charts. So, quantum tunneling travel remains a thought experiment that pushes us to consider just how strange quantum mechanics can be. It reminds us that impossibility in classical terms doesn't always hold at the quantum level, though practicality is another story. For now, tunneling remains a microscopic trick we harness in electronics and nuclear physics. Whether it'll ever let us slip through cosmic barriers remains in the realm of wild imagination, fueling occasional sci-fi plots and philosophical musings about the flexible boundaries of reality. Panpsychism. Have you ever wondered if consciousness is more fundamental than matter? Panpsychism suggests that a spark of awareness, however tiny, might be present in all things, from electrons to rocks to entire galaxies. Rather than emerging only when brains get complex enough, consciousness in panpsychism is woven into the fabric of reality, permeating the universe at every level. One way to imagine it is to think of consciousness like charge. Just as elementary particles carry electric charge, maybe they carry a proto-consciousness. By the time you build up a human brain from countless particles, you get a high-level mind. But even a single particle might have a rudimentary experience, an incredibly simple, perhaps indescribable feel. This doesn't mean your phone or a table thinks thoughts like we do. But it raises the idea that consciousness isn't just an accidental byproduct of complexity. It's more fundamental. Philosophers have debated versions of panpsychism for centuries, and modern thinkers keep returning to it because explaining consciousness is notoriously tough. Neuroscientists show how brain processes correlate with awareness, but bridging the gap between physical processes and subjective experience remains a mystery, sometimes called the hard problem of consciousness. Panpsychism tries to solve that by placing consciousness at the start, not at the end. Critics argue that panpsychism can sound like magical thinking. If everything is conscious, how do we prove or disprove that claim? Proponents respond that any theory of consciousness is challenging to verify objectively, and panpsychism at least avoids the puzzle of how consciousness might erupt from non-conscious matter. Some scientists explore whether quantum mechanics or integrated information theory might provide a path to testing these ideas. Ultimately, panpsychism is more a philosophical stance than a proven scientific theory. Yet it sparks active debate because it reframes how we see mind and matter. Maybe they aren't so different after all. Even if you find it far-fetched, exploring panpsychism can illuminate the blind spots in mainstream explanations of consciousness. It challenges us to expand our perspective, reminding us that the nature of awareness remains one of the great frontiers, and that the universe could be more alive than we commonly imagine. Axions. Imagine a tiny, elusive particle that could help solve two cosmic puzzles at once: the strong CP problem in particle physics and the enigma of dark matter. That's the axion. Physicists hypothesize it as a lightweight particle that emerges naturally from certain symmetries in quantum chromodynamics, QCD. If axions exist in large numbers, they might make up a big chunk of the universe's missing mass. Why are they needed? QCD predicts that strong interactions should allow for certain kinds of charge parity, CP, violation, but we don't see that in experiments. This is the strong CP problem. One elegant fix involves a field whose value adjusts itself to suppress this CP violation. The excitations of that field would be axions, named after a popular laundry detergent because they cleaned up a theoretical mess. At the same time, astrophysical observations tell us most matter in the universe doesn't emit light. It's dark matter. Axions, being neutral and very light, could float through space almost unnoticed. They interact so weakly that huge numbers could exist without us detecting them, yet their combined gravity might shape galaxies. That makes them a prime dark matter candidate, alongside others like WIMPs, weakly interacting massive particles. Detecting axions is tricky. Researchers build elaborate experiments to see if axions can convert into photons in the presence of strong magnetic fields. These haloscopes, or helioscopes, aim to capture faint signals from axions either bound around Earth or streaming from the Sun. So far, no definitive sightings, but the search continues. If we find axions, it'd be a 2-for-1 triumph. We'd confirm a neat theoretical solution to strong CP issues and possibly identify dark matter. That would rewrite textbooks in particle physics and cosmology. Yet, even if axions exist, we must confirm they have the right properties and abundance to explain dark matter fully. So, axions remain a cosmic missing piece, an elegant answer to two long-standing puzzles. Their allure is that they slip so seamlessly into the frameworks we already have. If experiments finally spot them, it'll be a landmark discovery, revealing a hidden but pivotal ingredient in the universe's makeup and shedding light on the subtle balancing acts behind fundamental forces. Dark fluid. What if the mysterious dark matter and dark energy are really two faces of the same coin, a single entity sometimes called dark fluid? This idea aims to simplify our cosmic accounting, which currently says about 95% of the universe is dark, split between matter that doesn't glow, dark matter, and a force-accelerating expansion, dark energy. Perhaps one fluid changes behavior over time or under different conditions, appearing matter-like in some places and energy-like in others. To visualize it, think of water. In a cold environment, it becomes ice, solid, while in a hot environment, it becomes vapor, gas. A dark fluid model suggests that the same substance can clump together like dark matter in galaxies, but spread out like dark energy in large-scale voids. So, we might unify the explanation of two big cosmic puzzles. Why consider this approach? Current theories about dark matter rely on unknown particles, while dark energy is often explained by a cosmological constant or similar concept that's equally mysterious. Handling them separately may be correct, but it feels cumbersome, like having two big unknowns filling the cosmos. A single dark fluid that transitions between phases could be more elegant, giving one phenomenon that takes on different forms. However, building a successful dark fluid theory isn't easy. You have to match precise observational data, how galaxies rotate, how clusters form, and how the universe's expansion rate changes over time. If the fluid lumps too readily, it won't look like dark energy. If it doesn't clump enough, it won't replicate dark matter. Some proposed models, like Chaplain gas or unified dark matter, attempt to walk this fine line, but so far, there's no universal consensus. Even if dark fluid ideas haven't won the mainstream, they reflect scientists' willingness to think outside the box. The universe is complex, and we still lack direct evidence for either dark matter particles or the exact nature of dark energy. So, the concept of one fluid doing both jobs is at least plausible enough to keep exploring. Whether it's right or not, it broadens our search for simpler underlying principles that might tie these cosmic riddles together. Subluminal wormhole communication. When we hear wormhole, we often imagine hopping across light years instantly. But there's another line of thought, subluminal wormhole communication, where a wormhole is used to send signals or matter more slowly than light, or at least no faster than normal signals. This might sound odd. If you've got a wormhole, why not zip through it at faster than light speeds? The catch is that many theoretical studies suggest wormholes need exotic matter or negative energy to stay open. And even then, they might not allow FTL travel in a simple way. Consider it like building a tunnel under a mountain. Sure, you avoid the winding road over the peak, but if the tunnel is blocked in certain spots or if traffic is restricted, you might not actually travel faster overall. Subluminal wormholes propose that you can still benefit from a shortcut, but once you factor in setup or stability requirements, you might not beat a photon traveling outside. However, the route could offer other advantages, like secure messaging or bypassing certain hostile environments. Physicists sometimes explore if wormholes could be used just for signals, with the throat too narrow for a spaceship. Even then, you'd need exotic matter to stabilize it. And the minute you try to transmit a signal, you might cause the wormhole to collapse unless you carefully manage the energy flows. So, the big revelation is that wormholes might be so delicate that practical use demands stepping far away from the usual sci-fi notion of instantaneous travel. So, subluminal wormhole communication could revolutionize our sense of distance if it were stable, providing a permanent link between two distant regions. You might see a time delay, but you'd have an unbroken channel. Military or scientific missions could exploit that for data or supply lines, even if they're not zipping past the speed of light. Of course, all of this remains highly theoretical. We've never observed a traversable wormhole, subluminal or otherwise, but it highlights how wormholes don't automatically equal sci-fi warp gates. The physics is nuanced, and true FTL travel may be prevented by nature's constraints. Even a slow wormhole, though, would be a monumental breakthrough, proving that space-time can be engineered into a tunnel bridging distant points. if only we can master the extraordinary challenges involved. Space-time engineering. Imagine designing space-time almost like an architect designing a building, shaping curves and folds to serve specific purposes. That's the dream behind space-time engineering. Traditionally, we take the geometry of our universe as a given. We may build rockets or satellites, but we don't fundamentally alter the structure of space and time they move through. Yet advanced theories hint that if we ever harness exotic matter or enormous energy scales, we could manipulate space-time more directly. Think of it like sculpting clay. You might create domes or tunnels. In relativity, mass and energy shape space-time's curvature. So if you had negative energy or intense gravitational fields arranged cleverly, you might form a shortcut, like a wormhole, or a warp bubble for FTL-like travel. Realistically, generating such energy distributions is beyond us right now. Even shifting tiny bits of vacuum energy remains out of reach. So, space-time engineering ideas pop up in discussions of warp drives, wormholes, and closed time-like curves. They rely on solutions to Einstein's equations that look mathematically valid but require improbable amounts of negative energy density to remain stable. These exotic constructs remind us how flexible Einstein's field equations can be, at least on paper. One possible near-term angle might involve gravitational wave manipulation. If we can create or direct gravitational waves in the future, we might do microscale shaping of space-time, though it's a colossal engineering challenge. Another avenue is research on quantum fields and metamaterials. Maybe one day we'll find new ways to produce local curvature changes. Even if it starts small, every step we take might open bigger doors. Skeptics argue that talk of engineering space-time is more science fiction than reality, given our current energy and material limits. But history shows that bold theoretical concepts sometimes spark real progress. Space-time engineering may not happen next century or even next millennium, but the seeds are planted. It fuels our imagination about how advanced civilizations, if they exist, might travel or communicate, and it keeps us pushing the boundaries of physics. After all, rewriting the cosmic landscape would be the ultimate achievement in technology, forever reshaping our relationship with distance and possibility. Quantum chaos. We often associate chaos with classical systems like weather patterns or swirling fluids. Yet there's a branch of physics called quantum chaos that explores how quantum systems can exhibit chaotic behavior at certain levels. The phrase might sound contradictory. Quantum mechanics is typically about smooth wave functions and discrete energy levels, while chaos is about unpredictable motions. But upon deeper inspection, the two ideas can mesh in intriguing ways. A simple analogy is a pinball machine. Classically, each ball's path is sensitive to tiny changes in angle or position. Quantum mechanics replaces those trajectories with probability waves. While you won't see a ball bouncing around in the usual sense, the wave function can still display complex patterns that mimic chaotic scattering. Observables, such as energy levels, can exhibit patterns reminiscent of classical chaos, like random-looking distributions called Wigner-Dyson statistics. Quantum chaos is important because many real systems, atoms, molecules, or even black hole interiors, may sit on the boundary where quantum rules interact with chaotic dynamics. By studying quantum chaotic systems, scientists learn about how energy levels distribute, how wave functions localize or spread, and how classical chaos emerges from quantum rules in the limit of large systems. Some experiments with microwave resonators or ultra-cold atoms can simulate these conditions. This research also ties into quantum computing. If a system becomes too chaotic, controlling its quantum states might be difficult, leading to rapid decoherence. Yet harnessing certain forms of chaos could potentially offer novel computational tricks. There's also speculation about quantum chaos in black holes. relating to how information is scrambled behind the event horizon, a hot topic in the black hole information paradox. So, quantum chaos doesn't mean we can predict the unpredictable. Even on the quantum stage, outcomes are probabilistic, and chaotic influences might still render them extremely sensitive to initial conditions. Studying quantum chaos just reveals how subtle patterns underlie what might seem random, bridging the gap between classical unpredictability and quantum uncertainty. Overall, quantum chaos highlights that the line between orderly quantum systems and messy real-world processes can blur. It reminds us that nature can be both wave-like and chaotic, weaving these traits together into complex behaviors that continue to challenge our attempts to fully understand or predict them. Metastable vacuum states. Have you ever thought our universe might be resting on a cosmic shelf rather than the bottom floor? That's the concept behind metastable vacuum states. In physics, a false vacuum is a state that isn't truly at its lowest energy but appears stable for an incredibly long time, like a ball tucked into a shallow valley instead of rolling all the way down to the deepest valley. According to some interpretations of particle physics, our universe might be perched on such a shelf, teetering in a state that's nearly, but not absolutely, stable. In simpler terms, picture a marble on a table with a slight rim. It looks safe, sitting still, but if enough vibration or a nudge arrives, it could drop off to the floor below. Likewise, if a quantum fluctuation or a high-energy event triggers our universe's marble to slip into a truly stable vacuum, it might initiate a bubble of this new phase that races outward at nearly the speed of light. Everything inside that bubble would be governed by different physics, rewriting matter's behavior and potentially destroying all familiar structures. How likely is this? Some theoretical calculations suggest the parameters of the Standard Model, especially the Higgs boson's mass, place our vacuum near a boundary between stable and metastable. That's it. The timescales for decay might be unimaginably vast, longer than the current age of the universe by many orders of magnitude. Others argue that new physics could shore up our vacuum stability entirely. Despite the daunting notion of cosmic doom, metastable vacuum states fascinate scientists because they connect particle physics with cosmology, forcing us to question whether fundamental constants are truly set in stone. Experiments at particle colliders and observations in astrophysics continue to refine our understanding, showing just how precarious or secure our cosmic perch may be. At the end of the day, whether or not we're in a metastable state, the possibility underscores a central theme in modern physics. Our universe could be more fragile and contingent than it appears. While it might take extreme energies or rare quantum events to topple us from our shelf, it's a reminder that cosmic certainties sometimes hide deeper uncertainties beneath them. Black hole information paradox. Have you ever wondered if everything that falls into a black hole disappears forever? Or if something more subtle is going on? That puzzle is at the heart of the black hole information paradox. Classical physics suggests that anything crossing the event horizon is lost to the outside world, never to return. Meanwhile, quantum mechanics insists that information can't simply vanish. It must be preserved in some form. It's like burning a book. In everyday life, the information might seem destroyed. Yet quantum theory says if you had a perfect record of all the particles and radiation, you could, in principle, reconstruct the book. Black holes muddy the picture because the event horizon seems to be a one-way door. Stephen Hawking added another twist by showing black holes gradually evaporate through Hawking radiation. So, if a black hole completely evaporates, where does all that trapped information go? Physicists have proposed various resolutions. Some argue that the information seeps out slowly in the subtle patterns of Hawking radiation. Others propose new structures at or near the event horizon, like firewalls that store or transmit the data. Another angle suggests that we might have to rethink space-time at a fundamental level, maybe embracing the holographic principle, where everything inside is encoded on a surface at the boundary. Testing these ideas is tough. Observing real black hole evaporation takes longer than the current age of the universe for stellar mass black holes. Smaller black holes would evaporate faster, but we haven't found any primordial tiny black holes yet, if they exist at all. Instead, researchers rely on theoretical arguments, thought experiments, and analog systems in the lab, like analog black holes using fluids. Whichever way it resolves, the black hole information paradox drives us toward a deeper understanding of quantum gravity. It highlights the clash between relativity's seamless space-time and quantum mechanics' emphasis on preserving information. Finding a unified theory that satisfies both might finally solve this decades-old riddle, showing us how nothing is truly lost in the cosmic ledger, even when it crosses the threshold of a ravenous black hole. Teleportation of mass, hypothetical. Have you dreamed of stepping into a chamber and instantaneously appearing somewhere else? Star Trek style? That's the allure of mass teleportation. While quantum teleportation is real, it only transfers quantum information, the state of particles, not the particles themselves, let alone entire objects. So, some visionaries wonder if future physics might enable actual mass teleportation, bridging vast distances in a flash. To clarify, quantum teleportation leverages entanglement to transmit the state of one particle onto another. It doesn't beam the original particle physically across space. Teleporting a human, or any sizable object, would require scanning every atom, quantum state, and arrangement, sending that data, then reconstructing it somewhere else. The original might need to be destroyed to avoid having two identical copies, an idea that raises ethical and philosophical questions. Is the reassembled you truly the same person? An analogy is scanning a book, emailing the file, then printing a replica at the destination. For everyday items, that might be fine. But for living beings with consciousness, it's trickier. Would the teleported version really be you, or just a perfect clone? Moreover, scanning and transmitting that much data at the quantum level is unimaginably complex. Even ignoring the philosophical dilemma, we lack technology to reliably measure and replicate each quantum state without destroying or decoring it. Some theoretical frameworks also speculate about shortcuts through space-time, like traversable wormholes, which might act as teleportation gates, physically relocating matter in an instant. But these rely on exotic matter and negative energy, which remain unverified in labs. If we ever achieve that engineering feat, we'd effectively have a method to transport mass without traveling the normal route. Yet, calling it teleportation might stretch definitions, as you'd still be moving through a specially engineered corridor of space-time. For now, mass teleportation stays firmly in science fiction. Nonetheless, exploring it sparks vital questions about identity, information, and the ultimate limits of technology. It pushes us to consider just how tied we are to our physical forms and whether physics will always confine us to conventional travel. Even if the final answer is no, such speculation reminds us how quantum leaps can reshape our most basic assumptions about distance and existence. Superluminal tunneling. Ever heard about experiments suggesting particles can tunnel faster than light through a barrier? That's the notion of superluminal tunneling, a phenomenon that has captured headlines and confounded scientists in equal measure. Quantum tunneling allows a particle to appear on the other side of an obstacle without having the classical energy to climb over it. In some lab tests, researchers noticed that the tunneling particle's arrival time seemed quicker than light would take across the same distance. It's important to clarify that this doesn't violate Einstein's special relativity. While the measured group velocity during tunneling can exceed the speed of light. There's no actual signal or information traveling faster than light from start to finish in the usual sense. The reason is tied to wave mechanics. The part of the wave function that emerges isn't necessarily carrying the original payload of information in a straightforward manner. One analogy is a river with a series of stepping stones. The wave function might skip across stones in a non-intuitive way. Observers see the outcome and think it's a direct route, but in reality, the wave function's evolution doesn't simply replicate a superluminal crossing. Another comparison is flipping through TV channels. Sometimes you jump from one station to another, skipping the intermediate frequencies, but you didn't physically travel faster than light in the electromagnetic spectrum. So, superluminal tunneling attracts attention because it underscores how quantum mechanics can produce results that look faster than what we'd expect from classical constraints. People sometimes misinterpret these findings, believing they can send messages into the past or outrun a beam of light. The consensus among physicists is that no real conflict arises with relativity once you account for how wave functions transmit actual information. Despite not enabling FTL messaging, superluminal tunneling is intriguing. It pushes us to examine how we define velocity and information transfer in quantum systems. Such studies can also refine our understanding of barrier penetration and wave function dynamics, crucial for technologies like quantum computing or tunneling microscopes. In that sense, superluminal tunneling remains a fascinating reminder that quantum phenomena often defy plain old common sense, yet still obey deeper physical laws. Dark energy propulsion. Picture harnessing the very force that's pulling galaxies apart to propel our spacecraft. A bold idea called dark energy propulsion. We know the universe's expansion is accelerating, likely driven by something we label dark energy. If we could somehow tap into that cosmic push, perhaps we'd zip through interstellar space without traditional fuel. Visualize a rubber band being stretched on all sides. Galaxies, like beads on the band, recede from each other as space expands. Now imagine tying your spacecraft to that expansion, so the expansion itself tugs you along. That's the dream. But the challenge is that dark energy is diffuse, with a density so low that even on galactic scales, its effect is subtle, dominating only at huge distances. Gravity, electromagnetic forces, and other effects usually overshadow it. Some propose advanced theoretical drives that manipulate local space-time expansion. You might try to create a bubble around your ship where dark energy is denser, generating repulsion. But the math and engineering are purely speculative. We'd need negative energy or exotic matter to shape the vacuum in ways we don't know how to do. Another angle is the concept of a cosmic sail, akin to a solar sail but pushing against the expansion of space, hoping to ride the universal tide. Yet again, the actual force is so tiny that it's unclear how you'd get a meaningful push. Furthermore, as you get deeper into space, you don't necessarily outrun the local gravitational fields that remain far more potent than dark energy at short ranges. So, dark energy propulsion remains an appealing notion because it challenges us to consider the largest forces in the universe as potential engines for exploration. With normal chemical or nuclear rockets, interstellar travel is daunting. It takes enormous fuel and time. If we discovered a trick to harness cosmic expansion, we might circumvent some constraints. For now, scientists see dark energy as a theoretical impetus for cosmic acceleration, not a practical rocket fuel. But it's part of a broader push to think big about propulsion. From warp drives to wormholes, we keep hunting for that groundbreaking leap. Who knows, perhaps in the far future, we'll devise ways to tug on the very fabric of space-time, turning the universe's grand push into our cosmic highway. Mobius universe models. Imagine unfolding the cosmos and discovering it's shaped like a one-sided loop, a bit like a Mobius strip. That's the inspiration behind Mobius universe models, which toy with the idea that the universe might have a non-orientable topology. A Mobius strip is easy to create. Twist a paper strip and tape the ends together, and you get a surface with only one side. If our 3D space had such a property, traveling a grand loop could invert your orientation, leading to all sorts of exotic possibilities. For instance, you might set off in one direction, and after a huge journey, come back flipped, like a mirror image. This might be too subtle to notice on a short trip, but could have implications for cosmic geometry and how fundamental fields behave. Non-orientable universes often arise in advanced topology discussions of general relativity, though they're not mainstream ideas. Nonetheless, they demonstrate that the shape of space-time can be far more peculiar than a simple infinite expanse or a finite but unbounded sphere-like shape. One analogy is to think of an ant crawling on a Mobius strip. It has no idea it's being turned around halfway through its journey. Only after it returns to the starting point, upside down, does the weirdness become evident. Similarly, if the cosmos had a Mobius-like structure, we'd need enormous loops or observations of distant light paths to detect orientation flips. Perhaps we'd spot patterns in the cosmic microwave background or unusual lensing effects. Skeptics note that a Mobius universe might conflict with certain data or require unusual boundary conditions. We haven't seen obvious signposts, so the fact we haven't detected it yet doesn't rule it out entirely. Some topologies are incredibly subtle. It's one reason why cosmologists keep an open mind, scanning large-scale structures and cosmic background radiation for the faintest anomalies. In the end, Mobius universe models remind us that geometry doesn't have to be normal. Einstein's equations are flexible about global shapes, and if you throw in exotic matter or boundary conditions, you can get surprising outcomes. Studying them expands our sense of what space can be, hinting that the greatest twist of all might be embedded in the very cosmos we inhabit. Pre-Big Bang cosmologies. Have you ever wondered if something existed before the Big Bang? Pre-Big Bang cosmologies dare to reach beyond that initial singularity, suggesting that our universe might have emerged from a prior phase rather than starting from nothing. In standard Big Bang theory, we trace everything back to an extremely hot, dense point around 13.8 billion years ago. But what if that's just the midpoint of a much older cosmic story? One scenario is the Big Bounce, where a previous universe collapsed under its own gravity until it hit a high-density state, then rebounded into expansion, our current universe. Imagine a trampoline. When you push down, you eventually reach a limit where the fabric pushes you back up. This cyclical model hints that the cosmos might undergo repeated expansions and contractions. Each Big Bang could be a bounce from a previous era. Others propose a pre-Big Bang phase driven by string theory or quantum gravity effects, where time existed long before, but in a state we can hardly imagine, like a low-density vacuum that suddenly transformed, triggering inflation and setting the stage for our current cosmic evolution. These ideas sometimes require exotic physics beyond our tested theories, but they offer ways to sidestep the singularity problem, where densities become infinite. Evidence for a pre-Big Bang phase is tricky to obtain. Most data about the early universe, like the cosmic microwave background, stems from a fraction of a second after the Big Bang. If any echoes from a prior epoch exist, they'd be subtle or heavily altered by inflation. Scientists keep an eye out for anomalies in cosmic radiation or gravitational wave signals that might hint at earlier cycles. Pre-Big Bang cosmologies fascinate us because they rewrite the question, why did it all begin? Into, does it ever truly begin? Rather than a strict beginning, time might extend backward indefinitely, with our universe just one chapter in an ever-unfolding saga. Though speculative, these models push the boundaries of what's possible, reminding us that the Big Bang, once thought of as the absolute start, might itself be part of a grander, more ancient cosmic dance. Quantum biology. Ever marvel at how birds navigate or how photosynthesis is so efficient? Quantum biology suggests that at least some biological processes might harness quantum phenomena like coherence or tunneling. Normally, we assume quantum effects get washed out in warm, messy environments like living organisms. But certain systems show hints that molecules could maintain delicate quantum states long enough to influence chemistry or behavior. Take photosynthesis. Plants and algae convert sunlight to energy with near-perfect efficiency, partly because the energy from absorbed photons travels through pigment molecules in a way that seems to use quantum coherence. Instead of meandering around randomly, the excitation might sample multiple pathways at once, choosing the best route. That's akin to how a quantum computer tries all possibilities simultaneously, then picks the optimal solution. Another famous example is bird navigation. Some species, like the European robin, navigate using Earth's magnetic field. A proposed mechanism involves cryptochrome proteins in their eyes that form radical pairs with unpaired electrons. These electron spins might be entangled, meaning their internal states correlate in a quantum way, helping the bird sense subtle magnetic cues. It's as if the bird sees a faint map guiding its flight south. Critics argue that while quantum effects can occur, they may not be widespread or stable enough to drive core processes of life. Yet ongoing research reveals that nature is cunningly adept at exploiting even fragile phenomena when it confers a survival advantage. Scientists try to replicate these findings in the lab, using ultra-fast spectroscopy to catch fleeting quantum beats in photosynthetic complexes or to measure spin states in proteins. Quantum biology's implications are profound. If life can harness quantum mechanics, then maybe we can learn from it, building better solar cells, sensors, or quantum-inspired devices. It also challenges our assumption that biology is purely classical, opening the door to more integrated theories bridging life sciences and quantum physics. Whether quantum biology is a rare trick or a fundamental aspect of life remains under investigation, but it's a testament to nature's ingenuity that such delicate quantum processes might thrive in the very environment we once thought too noisy for them. Anti-gravity. Have you imagined an engine that levitates objects by reversing gravity's pull? That's the notion of anti-gravity, a hypothetical effect that would repel rather than attract masses. In everyday experience, gravity is relentless. All massive bodies attract each other. But science fiction and far-out theories sometimes propose negative mass or exotic fields that could flip gravity into a repulsive force, letting us hover ships or build floating cities. While general relativity doesn't predict a standard mechanism for anti-gravity, it does permit regions with negative energy density, which might, in principle, create repulsive gravitational effects. But verifying or generating such negative mass distributions is beyond our current technology. Moreover, cosmic observations show repulsive-like behavior on large scales. Dark energy is pushing galaxies apart. But that's more about space-time expansion than a local anti-gravity force we can harness. One analogy is to picture magnets. They repel if you align their poles correctly. People wonder if mass could do something similar, but mass and electromagnetic charge aren't the same. We can flip a magnet's polarity easily, but mass polarity remains stubbornly positive in all known matter. Some theoretical approaches, like certain modified gravity theories or the concept of graviphotons, attempt to weave anti-gravity ideas into physics. Yet no laboratory has produced a material with negative inertial mass that would genuinely repel Earth. That said, anti-gravity crops up in serious discussions about advanced propulsion or warp drives, because repelling geometry might enable wormholes or warp bubbles. If you can't push matter away from you, maybe you can push space-time itself. Engineers and inventors have tried to crack the code with anti-gravity devices, but none have passed rigorous tests. Even if we never realize a true anti-gravity machine, the quest spurs creative thinking about how gravity might be manipulated. It reminds us that, for all we know, we're not close to exhausting nature's possibilities. Whether anti-gravity remains a pipe dream or a potential leap in propulsion technology, it's an iconic example of how we keep pushing the boundaries of what's possible, hoping to bend the fabric of reality to our advantage, even if, for now, gravity seems content being a one-way pull. Scalar field dark energy. Ever wondered what's truly driving the universe's expansion to speed up? One candidate is scalar field dark energy, which posits a smooth, dynamic field filling space. Instead of a constant cosmological constant, a scalar field can evolve over time, potentially explaining why dark energy's effects might have changed throughout cosmic history. Think of a rolling landscape. A scalar field is like a ball rolling on a potential hill or valley. If it's near the top, it can cause rapid expansion. Over time, it might roll to a new configuration, altering the expansion rate. This approach offers flexibility. Maybe dark energy was weaker in the past and becomes stronger in the future, or vice versa. That leeway can better match some observational data, though it complicates the model compared to a simple cosmological constant. An analogy is adjusting the flame under a pot of water. If you keep a constant flame, the boiling process is steady. If you turn the knob, you can change the rate at which the water heats or cools. A scalar field is like that adjustable knob, controlling how quickly space stretches. The question is, what sets the knob's rules? Some link these fields to high-energy physics, string theory, or extra dimensions that might define the field's shape and behavior. Measuring scalar field dark energy is tricky, as we mostly observe its effect on the expansion. Astronomers analyze supernova distances, galaxy clusters, and the cosmic microwave background to see if the data fits a changing dark energy equation of state. If it does, a dynamic scalar field may be favored over a static cosmological constant. So far, the data doesn't conclusively prove either side, leaving room for both interpretations. The search for direct signs of scalar fields, like new particles or couplings, is ongoing. Some labs look for fifth forces or slight deviations in gravity. While evidence remains elusive, the concept underscores how cosmic acceleration might be more than a bare constant. Perhaps an underlying field, gently shifting as the universe expands, orchestrates the grand expansion. If confirmed, we'd reshape our understanding of the vacuum's properties and the ultimate fate of the cosmos, revealing the subtle interplay between high-energy physics and the largest-scale structure we know. Time dilation hacking. Imagine slowing time for yourself so you can get more done, or speeding it up in a specific region to fast-forward a tedious process. Such a notion might be dubbed time dilation hacking, referring to artificially inducing strong relativistic effects to manipulate how fast clocks tick. We already know that traveling near light speed or hanging around a massive object can slow time relative to elsewhere, a well-tested result of Einstein's relativity. But using that effect deliberately to hack time for personal or industrial gain is another matter. A playful analogy might be stepping onto a super-accelerating treadmill that propels you close to light speed. While you was around, you experience less time than someone watching from outside. So a year might pass for them while only a few weeks pass for you. This could, in principle, let you skip forward in civilization's timeline if you're okay missing out on day-to-day life. Alternatively, you could place an experiment deep in a gravitational well to slow its clock, letting you gather more data in less time from an outside perspective. But building such extreme setups demands advanced technology and abundant energy. Futurists suggest applications like a time vault, where information or travelers experience less subjective time. Emerging far in the future, others consider industrial processes that require long durations, like aging certain materials, but for an outside observer, it's shortened. Yet the engineering challenges are huge. Achieving near light speed or harnessing huge gravitational fields basically requires cosmic-scale resources. Plus, any mechanical system under those conditions must survive intense stress. Critics also note the ethical and social implications. If someone invests in a time dilation bubble, they could leapfrog society or store resources. That scenario quickly veers into science fiction, but it underscores the theme that relativity isn't just a set of theoretical curiosities. It holds real potential for bizarre time strategies, at least in principle. Though we can't truly hack time for everyday convenience with current tech, thinking about it sheds light on how flexible the flow of time can be under relativity. Our everyday clock-based reality is only one slice of a bigger, more malleable picture. Maybe, far down the road, we'll see a new era where time manipulation, if not as easy as flipping a switch, becomes a frontier we can tiptoe across. Entropic gravity. Have you ever considered that gravity might not be a fundamental force at all, but rather an emergent property of entropy? That's the hypothesis behind entropic gravity. In this view, gravity arises because nature tends to maximize disorder, entropy, and what we call gravitational attraction is actually a statistical effect of particles rearranging themselves to increase the total number of possible configurations. Imagine a bookshelf with different compartments representing energy states. Over time, books get shuffled around, seeking a more probable arrangement. In entropic gravity, the positions of particles also shuffle to find states that maximize overall entropy. From a distance, this rearrangement looks like a force pulling matter together. The idea gained attention when physicist Eric Verland proposed a model linking gravity to entropy encoded on holographic surfaces. Why does it matter? If entropic gravity is correct, then general relativity might not be the final word on how space curves around mass. Instead, it could be a large-scale manifestation of deeper statistical rules about how information is stored in space-time. This approach might also help explain certain puzzles, like galaxy rotation curves without invoking dark matter, though that remains controversial. The analogy that often appears is a polymer chain in a container, which shortens when pulled from one end, reflecting a statistical preference. Translated cosmically, matter congregating is akin to that chain's entropic drive. Some see entropic gravity as bridging gravity and quantum information theory, giving a handle on phenomena like black hole thermodynamics in a more unified picture. Critics note that entropic gravity concepts need more rigorous tests. Many phenomena predicted by general relativity fit standard data well, and any emergent theory must match those results. Also, while entropic gravity might handle certain galaxy-scale observations, it's not fully proven to replicate all cosmic dynamics or unify seamlessly with quantum mechanics. So, the notion that gravity could be a side effect of entropy flips our usual perspective. It reminds us we're still exploring the bedrock nature of space-time, and that fundamental forces might themselves be emergent illusions. If entropic gravity holds even partial truth, it would reshape physics, merging thermodynamics, information, and geometry into a single tapestry that explains why objects fall, galaxies spin, and black holes burn with Hawking radiation. Neutron star materials. Picture matter so dense that a teaspoon would weigh as much as a mountain. That's the stuff neutron stars are made of, the compressed cores of exploded stars. Once a massive star runs out of fuel and collapses, its core can become a neutron star, packing the mass of our sun into a sphere just a few miles across. The question then arises, what is that material really like? deep inside? A good analogy is crushing an aluminum can until it's the size of a grain of sand, all while the atoms themselves fold in on each other. In neutron stars, protons and electrons combine into neutrons, so you essentially get a giant nucleus of neutrons with some leftover charged particles. The outer crust might be a lattice of neutrons and protons embedded in a sea of electrons. Deeper down, you might find exotic states like superfluid neutron matter or nuclear pasta, imaginative shapes with names like gnocchi and spaghetti, reflecting weird nuclear structures. Studying neutron star material is challenging. We can't just scoop up a sample. Instead, astronomers observe signals like pulsar rotations, gravitational wave events from neutron star mergers, and X-ray emissions from hotspots on the star's surface. From these measurements, they glean clues about the star's internal makeup. For instance, how the star's crust cracks might cause starquakes that emit bursts of radiation. These investigations also tie into fundamental physics questions. At such extreme densities, the nuclear force is pushed to its limits, and quarks might begin to roam freely, forming a quark-gluon plasma. Some hypothesize that the innermost core could be strange matter, containing strange quarks stable under immense pressure. Confirming or refuting these states would reveal new frontiers in quantum chromodynamics. Understanding neutron star materials isn't just academic. It can teach us about how matter behaves in superdense environments, possibly guiding fusion or other high-pressure physics on Earth. Plus, when neutron stars collide, they forge heavy elements like gold and platinum, seeding the universe. So, that ring on your finger might have once formed in a cosmic cataclysm from the heart of a neutron star. Indeed, these stellar remnants provide a window into the most extreme matter states nature can cook up, reminding us how powerful and inventive the universe can be when it comes to crushing stuff beyond recognition. Quantum infinity diversion. Have you heard that quantum field theories often produce pesky infinities in their equations? Physicists typically use a process called renormalization to handle them, subtracting out infinities to yield finite, predictive results. Yet some propose a deeper fix, quantum infinity diversion. Instead of patching equations with renormalization, maybe we can devise a framework where these infinities never arise, or are automatically diverted, by changing how we view space-time or particle interactions. Picture a library catalog that indexes an infinite number of books. If you keep them all in one place, it's overwhelming. But if you have a clever filing system, you might divert or redistribute them so each section remains manageable. Likewise, quantum infinity diversion might reorganize the underlying mathematics so that infinite sums neatly converge or cancel out. This approach touches on ideas like string theory, where tiny vibrating strings replace point particles. Because strings have a finite length, the worst divergences might vanish. Loop quantum gravity also tries to quantize spacetime so it's not a continuum that spawns infinite energies at arbitrarily small scales. Yet we don't have a single, universally accepted solution. Some physicists suspect that a complete theory of quantum gravity will inherently handle these infinities, perhaps in ways we can't yet imagine. Others believe we can keep using renormalization effectively, as it's been wildly successful for the standard model so far. The question is whether there's a more elegant system that sidesteps those infinite pitfalls altogether. An example is how black holes create infinite curvature at their singularities. Quantum infinity diversion might require rethinking singularities so they're replaced by finite states. This goes hand in hand with the search for singularity-free models of the Big Bang or black hole cores, tying cosmic extremes to quantum fundamentals. While we wait for breakthroughs, the infinite sums remain part of the standard toolkit. They do hamper direct unification of gravity with quantum mechanics, though, since naive attempts blow up with infinite values. Ultimately, quantum infinity diversion is about re-engineering the core of our theories so that reality's building blocks can play nicely without generating nonsensical math. If achieved, it could reshape our view of space-time, forces, and matter at the most profound level. Negative refractive index. Picture shining a flashlight on a prism, and instead of bending light in the usual way, it bends backward, a phenomenon known as negative refraction. That's what materials with a negative refractive index can do, defying our everyday experiences of how light behaves. Normally, light slows down and bends when entering a denser medium, but in a negative index medium, it veers in the opposite direction, producing effects like reversed Snell's law. A helpful analogy is driving a car onto a highway ramp that slopes in reverse. Rather than steering it forward, the ramp might tilt it backward. In negative index materials, the internal structure is engineered so that electromagnetic waves respond oddly to the arrangement of atoms or microstructures. Essentially, the electric and magnetic fields in the wave interact in a way that sends the wave traveling the wrong way. Scientists first achieved negative refraction using metamaterials, which are artificial constructs with carefully designed patterns smaller than the wavelength of light. By arranging tiny circuits or resonators, researchers create properties not found in nature, such as negative permittivity or permeability. It opened the door to advanced optics, superlenses that exceed the diffraction limit, potentially capturing finer details than ordinary lenses, and even suggestions of invisibility cloaks that guide light around an object. However, practical challenges remain. Early negative index metamaterials worked mostly at microwave frequencies. Extending them to visible light demands nanometer-scale precision. The materials also often suffer from high losses, meaning they absorb a lot of the incoming light. Researchers continue refining designs to reduce absorption and broaden the frequency range. If they succeed, negative refraction could revolutionize everything from imaging systems to stealth technology. While you won't see everyday bend backward glass windows soon, negative refractive index metamaterials exemplify how controlling wave interactions at subwavelength scales can yield truly exotic effects. They highlight the creativity of modern physics and engineering, revealing that impossible optical properties become possible if you tailor matter at the right scale. Beyond just a novelty, negative refraction points the way to next-level manipulation of light, with impacts on microscopy, telecommunications, and even fundamental research on how waves move through unusual media. Stochastic Electrodynamics. Hope can arise from the idea that our seemingly random universe might be guided by underlying classical fields. That's the core spirit behind stochastic electrodynamics, SED. This alternative framework suggests that instead of relying on the full machinery of quantum mechanics to explain phenomena like the Casimir Effect or zero-point energy, we could interpret them in terms of classical electromagnetism infused with a random background field. To draw a comparison, imagine a pond surface on a windy day, rippling with waves. Particles are like little boats that experience random jostles from an all-pervading electromagnetic field. Where quantum theory says particles have inherent wave functions, SED attributes those wave-like behaviors to continuous interactions with fluctuating fields. The result is that phenomena normally chalked up to quantum weirdness might, in principle, be explained using classical ideas, albeit with a dash of randomness that's not so random once you accept the background field as real. Proponents of SED point out that it captures certain phenomena, such as the stability of atomic orbits, by treating electrons as being constantly buffeted by zero-point electromagnetic fluctuations. They propose that this ongoing jiggle could prevent electrons from spiraling into the nucleus. While quantum mechanics achieves the same result with wave functions and the Heisenberg uncertainty principle, SED tries to show that a classical-based approach might replicate or approximate some quantum predictions. However, mainstream physics has yet to embrace SED as a comprehensive replacement for quantum theory. Some critics argue that SED runs into inconsistencies or struggles to match the full range of quantum experimental data, especially those involving entanglement or Bell's inequalities. They see it more as a curious reinterpretation than a truly rival theory. Nonetheless, research continues, with SED-inspired models occasionally popping up to explore vacuum phenomena or potential connections to subquantum structures. Where does hope lie here? For some, it's in the possibility that the conceptual gap between quantum and classical pictures could be bridged, revealing a deeper, deterministic structure beneath quantum laws. Whether SED succeeds or not, it highlights that even well-established theories may have alternative interpretations, reminding us that our quest to understand reality always leaves room for creative rethinking and hidden layers in the classical versus quantum debate. Hypercomputation. A glimmer of hope shines whenever we ask if there's a way to compute the uncomputable. Hypercomputation explores this tantalizing possibility, challenging the notion that Turing machines, our gold standard for computation, define the ultimate limits of what can be calculated. In classical computer science, the Church-Turing thesis states that anything computable in the physical universe can be replicated by a Turing machine. Yet hypercomputation posits systems that could, in theory, solve problems no Turing machine can handle, like the notorious halting problem. Imagine a device that can process infinite steps in finite time or exploit inaccessible oracles that instantly answer certain undecidable questions. One thought experiment involves supertasks, where you compress an infinite sequence of operations into a finite interval, reminiscent of Zeno's paradoxes. Another approach uses unorthodox physics, such as diving into a black hole's event horizon to harness infinite time dilation for computations. While these ideas strain credibility or practical feasibility, they illuminate how flexible the concept of computation can be if we allow exotic scenarios. Critics often point out that hypercomputation might be physically impossible, requiring infinite energy, negative mass, or other unrealistic conditions. In mainstream science, no experiment suggests we can surpass Turing computable processes in real-world conditions. Nonetheless, hypercomputation intrigues philosophers and theoretical computer scientists by pushing the boundaries, maybe in a higher dimensional or cosmological setting, or with quantum gravity tricks, we could outrun standard computational limits. Where does hope fit in? If hypercomputers were feasible, we might tackle problems like automatically proving or disproving any mathematical statement, or quickly cracking encryption that's classically unbreakable. We could unravel scientific models currently stuck behind intractable computations. Of course, that's a big if. Most suspect hypercomputation remains in the realm of thought experiments, not future hardware announcements. So, even if actual hypercomputers never appear, exploring them challenges our assumptions about physics, computation, and logic. It reminds us that our definitions of possible rest on the known laws of nature, which themselves might evolve. So, whether hypercomputation stands as a whimsical dream or a hidden reality, it underscores humanity's unending drive to surpass the frontiers of knowledge, always probing whether infinity can be harnessed in ways once deemed unthinkable. Exotic rotating universe. Hope springs from the idea that the cosmos might have once spun on a grand scale, an exotic rotating universe scenario. Normally, we learn that the universe is either expanding uniformly or possibly curved, but not rotating overall. Yet certain solutions to Einstein's field equations allow for large-scale cosmic rotation, akin to the Gödel Universe. In these exotic models, Space-time itself is twisted in such a way that an observer traveling far enough could return to their own past, implying closed time-like curves. Imagine you could stand on a cosmic vantage point and see the entire sky pivot around you, not just due to local star motion, but because the very geometry of space-time is swirling. On smaller scales, we know galaxies rotate, and clusters may have net angular momentum. Extrapolate that up to cosmic scales, and you get a swirling, rotating cosmos. The question is whether inflation and cosmic evolution would damp out any large-scale spin, or if some leftover swirl might persist as a subtle signature in the cosmic microwave background, CMB. Scientists have searched for directional patterns in the CMB that might imply cosmic rotation but haven't found conclusive evidence. If we did spot a swirling pattern, that would be a seismic shift in cosmology, revealing an entire new layer of structure to the universe. It might also open the door to speculative phenomena like time loops or a unique distribution of matter and antimatter. Indeed, a rotating universe might give hints about how matter organizes or why certain asymmetries exist. Of course, most mainstream models assume no significant rotation overall. Observations strongly suggest isotropy, meaning the universe looks the same in every direction. Even a tiny rotation rate, if real, would have left subtle imprints on large-scale structures. With continuing improvements in cosmic surveys, if any rotation exists, it must be extremely small. But that doesn't stop researchers from exploring the math or wondering if corners of the cosmic evolution might involve swirling boundary conditions. The hope in exotic rotating universes is that they remind us we can't assume the cosmos is entirely uniform or free from rotation just because we don't see it easily. Each new test that rules it out with higher precision also confirms how well standard cosmology stands. And if we ever detect even the smallest swirl in the cosmic tapestry, it could spark a revolution in how we perceive time, structure, and cosmic destiny itself. Cosmic microwave background manipulation. Hope arises when we imagine manipulating the very afterglow of the Big Bang. The cosmic microwave background, CMB, is like a faint whisper of radiation permeating space, a near uniform backdrop from when the universe cooled enough for electrons and protons to combine into neutral atoms. But what if an advanced civilization, or future human technology, could shape or harness this ubiquitous radiation for communication or energy? Visualize the entire sky lit by a subtle glow of microwaves. In principle, if you had a massive network of satellites or metamaterials spread across solar system scales, you might focus or modulate regions of the CMB. This could theoretically create patterns or signals visible to distant observers who measure small deviations in the background's uniform temperature. The concept is reminiscent of building colossal cosmic billboards. But the scale is staggering. Our current technology is nowhere near such feats, and we face tremendous engineering and energy barriers. Another possibility is using the CMB as an energy reservoir. While it's extremely diffuse, just under 3 Kelvin, someone might propose pumping heat from a warmer region into the cold background, generating electricity via temperature differentials. This might be akin to a cosmic heat engine that runs between the warmth of local structures and the nearly absolute cold environment of deep space. However, the second law of thermodynamics and practical efficiency constraints mean this yield would be minuscule per device. So, in an extremely advanced future, or for hypothetical Kardashev Type 3 civilizations, altering or employing the CMB might be trivial. They could, for instance, manage galaxy-sized structures to glean useful work from slight differences in cosmic temperature. They could also embed data or signals into the background, effectively turning the entire cosmos into a communication channel. Right now, cosmic manipulations remain in the realm of speculation. Yet discussing them broadens our perspective on what might be achievable over astronomical timescales. It also reveals how precious the CMB is as a relic that unveils our universe's baby picture. Any tampering by advanced beings would be a cosmic signature indeed, one that could revolutionize our understanding of intelligence, energy, and the scale at which civilizations might operate across the galactic stage. Fractional dimensional spaces. Hope can emerge from the idea that dimensions need not be whole numbers. In certain mathematical frameworks and physical theories, fractional dimensional spaces arise, suggesting that reality might operate in a fractal-like geometry with dimensions between integers, rather than living in strict 1D, 2D, or 3D realms. Some processes might live effectively in, say, 2.5 dimensions. Imagine a coastline that looks smooth from far away but reveals complex, self-similar patterns up close. In fractal geometry, you can measure the coast dimension as somewhere between a line, 1D, and an area, 2D. Extend that to the quantum or cosmic scale, and you might discover that the structure of space-time or certain fields is fractal. For example, a wave function might spread out with fractional dimension, influencing how particles traverse the quantum realm. Researchers have used fractional calculus to describe anomalous diffusion in disordered materials, where molecules wander in a fractal-like environment. In some advanced quantum gravity models, near the Planck scale, spacetime's effective dimension might drop below 4, impacting how particles interact. Observations in cosmic rays or black hole thermodynamics might one day hint that the dimension of space changes with scale. The notion of fractional dimensional spaces also influences computational algorithms, with fractal-based techniques used in data compression or computer graphics. By acknowledging that real-world phenomena sometimes follow fractal patterns, we can refine simulations of turbulence, growth processes, or neural networks. Each success story hints that fractional dimensions are more than just a math curiosity. Critics argue it's a stretch to say the universe truly has fractional dimensions. Maybe these are just approximations for complicated shapes. Even so, exploring fractional geometry helps unify our descriptions of nature's complexity. A fractal perspective can bridge biology, geology, and astrophysics, revealing patterns that appear across vastly different scales. Ultimately, fractional dimensional spaces remind us that dimension isn't always a rigid property. Reality may be more flexible, shaped by recursive or self-similar structures. This opens up a realm of possibility, suggesting we can keep refining how we classify the shape and nature of both the smallest quantum realms and the largest cosmic structures. In that sense, acknowledging fractional dimensions is a humbling testament to nature's creativity in forging patterns beyond simple integer boundaries. Cloning theorem, quantum. Hope sometimes arrives as a surprising limit, reminding us how special quantum information truly is. The quantum no-cloning theorem states that you can't make a perfect copy of an unknown quantum state. In classical computing, duplicating files is trivial, but in quantum mechanics, attempts to clone an unknown state unavoidably disturb it or yield a flawed copy. This result underscores how quantum information is more delicate than its classical counterpart. Picture trying to photocopy a painting that has hidden, subtle brushstrokes. The photocopier automatically alters the strokes in unpredictable ways. In quantum terms, measuring a state partially collapses its wave function, so you don't get a full record of it to replicate. This built-in feature prevents phenomena like infinite eavesdropping in quantum encryption. If someone tries to intercept a quantum message by copying it, that intrusion can be detected. This theorem also influences futuristic sci-fi dreams of Star Trek-style teleportation. True quantum teleportation transmits only the state of a particle, destroying the original in the process. The no-cloning rule keeps you from producing duplicates all over the cosmos. Similarly, it protects quantum cryptography, ensuring that quantum-encrypted info can't just be cloned and cracked offline. This is a boon for secure communications, fueling interest in quantum key distribution. But why might a limitation be a source of hope? Because it reveals that quantum mechanics helps preserve privacy in ways classical systems can't. It also forces us to get creative with quantum computing and communication protocols. We can't rely on copying data the way we do with classical bits. Instead, we craft new error correction methods or design cunning methods like entanglement swapping to move quantum information without duplication. Critics might note that approximate copies can be made, just not perfect ones. Indeed, certain cloning machines produce partial fidelity but never a flawless twin. This subtlety reaffirms that the no-cloning principle is about perfection. The bigger takeaway: quantum phenomena carry inherent security features and constraints that shape how we develop technology. It's a gentle reminder that quantum reality is uniquely safeguarded by the laws of physics, offering both challenges and remarkable opportunities for secure communications, quantum computing, and beyond. Supersymmetry, SUSY. Hope for a grand unification often centers on supersymmetry, or SUSY for short. This theoretical framework proposes a partner particle for every known particle, linking bosons, force-carrying particles, with fermions, matter particles. In the standard model, these two classes remain distinct, but supersymmetry unites them under one larger symmetry, suggesting they're just two faces of the same coin. Imagine you have two puzzle pieces that appear mismatched. SUSY says there's a deeper structure that pairs them up. Each quark or electron would have a squark or selectron, while each gauge boson would have a gaugino. If this new symmetry holds, it might solve nagging problems like the hierarchy problem, explaining why the Higgs boson's mass is so small compared to the Planck scale. In principle, superpartners could cancel out quantum corrections that would otherwise blow up the Higgs mass. Physicists also see SUSY as a prime candidate for explaining dark matter. One of these superpartners, possibly the lightest neutralino, could be stable and weakly interacting, matching the profile of dark matter. Discovering superparticles at colliders would be a twofold triumph: evidence for unification and a resolution of the cosmic puzzle of invisible mass. Yet, the Large Hadron Collider has not found direct evidence of low-energy SUSY so far, leading some to question if superpartners lurk at even higher energies or if SUSY might be realized in a more subtle manner. Critics say the lack of sightings is disheartening, but proponents counter that the parameter space is vast, and we may not have probed the right corners yet. Despite the challenges, SUSY remains deeply appealing because it elegantly merges multiple lines of inquiry. It tidies up quantum corrections, offers a dark matter candidate, and points toward deeper unifications with string theory. Even if the simplest versions are ruled out, more complex variants might still be realized in nature. The hope is that soon, next-generation colliders or improved astrophysical observations will shed light on whether supersymmetry is truly woven into our universe's fabric. If so, it would mark a watershed moment, one step closer to a cohesive, all-encompassing theory of matter and forces. Metastable exotic atoms. Hope can sparkle when we think of building atoms out of unusual components, forming exotic atoms that last long enough to explore. Metastable exotic atoms replace one or more electrons with heavier or rarer particles, like muons, pions, or even antiprotons. Though they're not typically found in nature for extended periods, advanced labs can create them briefly, offering glimpses into novel chemistry and fundamental physics. Picture an atom where instead of an electron orbiting the nucleus, you've got a muon, similar to an electron but heavier. Because it orbits closer to the nucleus, the energy levels shift, revealing finer details about nuclear size and structure. In fact, muonic hydrogen measurements famously refined our understanding of the proton's radius, stirring debate known as the proton radius puzzle. Another example is antihydrogen, combining a positron with an antiproton to mirror normal hydrogen. Studying it can test fundamental symmetries, checking whether antimatter behaves identically to matter under gravity and electromagnetic interactions. Yet, these exotic atoms rarely live long. Muons decay into other particles, while antiprotons annihilate with normal protons if they venture too close. Researchers often rely on vacuum chambers and careful trap designs to keep these short-lived species alive just long enough to measure transitions or analyze collisions. Each success yields data that can refine quantum electrodynamics, reveal subtle nuclear effects, or test charge parity time, CPT, symmetry. Where does the metastability come in? Sometimes small effects, like transitions to less reactive states, prolong the atom's life. If we discover ways to coax these exotics into stable configurations, even for microseconds, that might open up new realms of exotic chemistry, with unknown properties or potential applications. Imagine harnessing the intense binding energy or unique transitions for advanced sensors or exotic materials research. Skeptics note that creating these atoms is costly, and sustaining them for practical tasks is a huge challenge. But each incremental improvement in experimental setups yields valuable insights, bridging nuclear, particle, and atomic physics. The quest for metastable exotic atoms stands as a testament to human ingenuity. Even ephemeral states can teach us about the deepest layers of matter, fueling the hope that if we can just keep them around a bit longer, they might unlock discoveries we never dreamed possible. Vacuum phase transitions. Hope blossoms when we consider that empty space might not be so empty after all, and could even change form in a snap. Vacuum phase transitions suggest that what we call the vacuum could shift from one energy state to another, like water freezing into ice. If our universe's vacuum is only metastable, a random event could trigger a new, low-energy phase, potentially rewriting the laws of physics and transforming everything. Think of a supercooled liquid that can remain liquid below its freezing point, yet crystallizes rapidly if it encounters the tiniest seed. Our vacuum might likewise hold back from transitioning to a true ground state. Once triggered, a bubble of true vacuum expands at near light speed, altering particle masses, force strengths, and more. As we know it, would be obliterated in that bubble. But not all vacuum phase transitions are doomsday scenarios. In the early universe, phase transitions likely shaped cosmic structure. For example, the electroweak phase transition allowed the Higgs field to switch on, giving particles mass. The details of such transitions left imprints in the cosmos, influencing inflation, baryogenesis, and gravitational waves. Even today, advanced detectors search for faint gravitational wave signatures from these cosmic events, hoping to peer back into the universe's infancy. On smaller scales, colliders replicate high-energy conditions, probing if new transitions occur under extreme energies. The nature of these transitions tells us if the vacuum is stable or perched precariously on a local minimum. Data from the Higgs boson's mass and couplings feed into these models, hinting our vacuum might be teetering at the edge of stability, although timescales for a catastrophic flip could be longer than the age of the universe. Where do we find hope here? First, it's humbling yet exhilarating that cosmic catastrophes or transformations might lurk as fundamental possibilities. Second, each experiment that refines our understanding of the Higgs sector and vacuum structure nudges us closer to a more confident cosmic forecast. Maybe we'll discover hidden phases that were crucial to cosmic evolution, or confirm our vacuum is stable. Either way, exploring vacuum phase transitions underscores how even nothingness can have profound, life-altering possibilities woven into its quantum tapestry. Muon-Catalyzed Fusion. Hope can flame from the concept of clean, abundant energy through muon-catalyzed fusion. Fusion itself is the process powering stars, where nuclei merge and release massive energy. Typically, achieving fusion on Earth requires extreme heat and pressure, as in tokamaks or laser ignition facilities. Muon-catalyzed fusion suggests a shortcut, using muons, heavy cousins of the electron, to bring nuclei closer together, bypassing some of the usual repulsion hurdles. Imagine you replace an electron in a hydrogen molecule with a muon. Because muons are heavier, the nuclei get pulled closer, making it easier for them to fuse. The concept is that the muon temporarily acts like a quantum glue, facilitating fusion at lower temperatures. Then, if the muon survives, it can move on to catalyze more fusions, like a match that can light multiple fireworks in sequence. Early experiments in the mid-20th century showed that muon-catalyzed fusion is real, but practical energy production remains elusive. One big issue: muons decay in about 2 microseconds. We need to create muons, which itself costs energy, and hope each muon triggers enough fusions to offset the production cost. Typically, each muon might catalyze only a few hundred fusions before decaying, falling short of break-even energy. Researchers have improved yields, but we're still not near a commercial reactor that runs on muon-catalyzed fusion. So, the idea retains fascination because of its elegance, a cold fusion-like approach that's actually grounded in legitimate physics. If technological breakthroughs massively reduce the energy cost of muon generation and keep muons from being lost prematurely, the door might open. Even if large-scale power production never comes to fruition, investigating muon-catalyzed fusion helps refine our knowledge of nuclear physics, quantum effects in fusion processes, and advanced accelerator technology. For some dreamers, each step forward is a spark of hope that maybe we'll eventually harness fusion at more manageable temperatures, skipping the monstrous magnetic or laser-based setups. That might be decades away, if feasible at all. But continuing to push the boundaries with muon-catalyzed fusion underscores our relentless quest for a stable, clean energy source to power the future. After all, even partial successes expand our scientific horizon, shedding light on how to orchestrate nuclear dance steps in ways nature typically only accomplishes in stellar cores. Ennians. Hope appears whenever we find new ways to classify the building blocks of reality. Ennions are particles in two-dimensional systems that defy the usual distinction of bosons and fermions. In 3D, quantum statistics says particles are either bosons, like photons, that can pile into the same quantum state, or fermions, like electrons, that obey the Pauli exclusion principle. But in 2D, there's room for an in-between. Ennions can have fractional statistics, where exchanging two particles yields a phase factor other than plus or minus 1. Imagine dancing partners who spin around each other. With bosons or fermions, the outcome is straightforward. You switch places in a single move. Ennions? However, let the dance be more nuanced, like performing a fancy loop, introducing additional phases in the wave function. This property can generate braiding phenomena, where how you move one ennion around another can drastically change the system's quantum state. Ennions first appeared in theoretical models of 2D systems, like the fractional quantum Hall effect, where electrons in thin layers under strong magnetic fields behave collectively. Over time, researchers gathered increasing evidence that these exotic quasiparticles really exist. More recently, experimental setups with ultra-cold atoms or specialized nanostructures have sought to directly observe ennions and confirm their braided statistics. Why is that hopeful? Anyons may enable topological quantum computing, which could store and process information in braids of anyons, making it inherently robust to local errors. Imagine weaving world lines of these quasiparticles so that the final braid encodes your computation. Tiny local disturbances can't easily disrupt the topological pattern, offering a form of built-in quantum error correction. Challenges remain in producing and manipulating anyons reliably. We also need clear, repeated demonstrations of fractional exchanges to prove their existence beyond a shadow of a doubt. But progress is steady. Each new experiment that spots fractional braiding or topological signatures gets us closer to harnessing these bizarre particles for next-gen computing. Ultimately, anyons expand our particle classification beyond the simple boson-fermion dichotomy, revealing new chapters in quantum mechanics. By bridging fundamental physics with practical applications, they embody the excitement that sometimes the weirdest theoretical predictions turn out to be real, and potentially revolutionary for technologies that exploit their novel stats. Hawking-Hartle no-boundary proposal. Hope emerges in a vision that the universe might not have a singular starting point at all. The Hawking-Hartle no-boundary proposal suggests that time and space could be finite but without a sharp boundary, no distinct moment we'd call the beginning. Think of the Earth's surface. It's finite, but you never stumble upon an edge. Similarly, in this model, as you trace back to the early cosmos, space-time smoothly transitions into a purely spatial region, removing the notion of a singular instant of creation. Stephen Hawking and James Hartle framed this idea using the concept of imaginary time, where near the Big Bang, time behaves more like a spatial dimension. In that realm, the universe can be described as a closed geometry, a rounded shape, rather than something that began from an infinite point. Once you pass a certain threshold, time transitions to the normal, real time we experience. This approach aims to resolve the traditional singularity problem in standard cosmology, where densities and curvatures blow up to infinity. An analogy is traveling north until you reach the North Pole. There's no boundary line that says you can't go any further. The direction just ceases to exist because the geometry changes. Similarly, with the no-boundary proposal, you never encounter a cosmic boundary. Time's arrow simply emerges as part of the geometry, like latitudes on Earth. Does this solve all cosmic mysteries? Not exactly. Critics argue about how well-defined the path integral approach is when applying imaginary time and whether the proposal fits all observational data. But it's an elegant attempt to unify quantum theory and general relativity in describing the Big Bang's origin without a singular cataclysm. The hope is that if the universe truly has no boundary in time, many philosophical questions about before the Big Bang become moot. The geometry might be self-contained. Meanwhile, observational cosmologists keep refining data to see if certain predictions about inflation or quantum fluctuations match. If future evidence aligns with no-boundary predictions, it would reshape how we think about cosmic origins, not a stark beginning, but a smooth horizon of space-time from which everything we know emerges naturally. Multi-stability of physical laws. Hope can be found in the idea that our known laws of physics might not be singular or locked in forever. The notion of multi-stability proposes that several different sets of physical laws could coexist under different conditions, just as water can be solid, liquid, or gas depending on temperature and pressure. Imagine a cosmic environment where phase transitions swap one set of fundamental laws for another, leading to drastically different universes or pockets within a grander multiverse. For an analogy, think of how a magnet can flip orientation when heated or cooled past a critical point. Similarly, if certain parameters in quantum field theories cross a threshold, the vacuum might shift from supporting one family of particles and interactions to another. This ties in with the concept of vacuum phase transitions, Except now we expand it to the very structure of laws, like how many dimensions are active, which symmetries hold, or whether certain fundamental constants change. Scientists sometimes place these ideas in the context of string theory or other high-level frameworks that allow multiple vacua or multiple solutions, each with distinct physics. Our familiar laws, like electromagnetism, strong nuclear force, or even the stable proton, might be just one branch, while other branches exist if you tilt the cosmic thermostat. If you drift into a region with a different vacuum, the fundamental constants might differ, or entire forces could vanish, rewriting how matter forms. Critics argue that we have no direct evidence for such radical changes in physical law. Observations so far suggest remarkable stability across cosmic time. But if the early universe or other cosmic domains underwent more extreme conditions, pockets of altered law might still exist out of our view. Moreover, even a slight shift in constants could cause galaxies, stars, and life to vanish. Yet the hope is that exploring multi-stability encourages us to remain open-minded about the uniformity of physics. If transitions between different law phases are possible, it would unify cosmic evolution, high-energy physics, and the Anthropic Principle in ways we haven't fully grasped. Whether or not we find direct clues, the concept inspires us to see that the laws we cherish might be placeholders in a bigger cosmic library, where entire shelves hold alternate rule books awaiting the right conditions to come alive. Quantum archaeology. Hope springs eternal in the dream that we might reconstruct long-lost past events from quantum traces, a field nicknamed quantum archaeology. Picture an advanced future civilization using the principles of quantum mechanics to comb through data stored in the environment, retrieving enough information to piece together historical scenes, maybe even resurrect extinct species or lost individuals. It's reminiscent of genealogical research, but on a cosmic, quantum scale. An analogy is how a forensic investigator collects scattered evidence to rebuild a crime scene. Quantum archaeology suggests that every particle interaction leaves behind subtle imprints in the wave function of the universe. If one had godlike computation power and precise knowledge of all quantum states, one might unravel the chain of events leading to the present, effectively replaying them. Some take it further, dreaming you could gather enough detail to recreate consciousness or resurrect past minds. That's heady stuff, part speculation, part philosophical puzzle. Skeptics quickly point out the immense data requirement. The universe is unbelievably complex and wave function records degrade under decoherence. Reconstructing even a small region's past would require more computational power than we can fathom. Additionally, quantum uncertainties might block perfect retrieval of prior states. Classical chaos alone can scramble data to near irrecoverability. Quantum processes intensify that difficulty, and any attempt to measure or record these quantum traces typically changes them. Nevertheless, quantum archaeology sparks debate about the nature of information in the universe. If quantum information is never truly lost, then perhaps in principle, a perfect snapshot of the past remains embedded in the universal wave function. That might align with the black hole information paradox resolution, where even black holes can't destroy info. The question is whether that info is practically accessible or locked behind cosmic-level entanglements forever. For some, the idea offers comfort. A cosmic library might exist, storing everything that ever happened. For others, it's science fiction that trivializes the real constraints of measurement, computation, and entropy. Yet it does highlight how quantum theory merges with big philosophical questions about memory, identity, and the irreversibility of time. Even if quantum archaeology remains purely hypothetical, it reminds us that the universe might hold deeper records than we ever imagined, beckoning us to keep exploring the limits of knowledge. Emergent Space-Time. Hope glimmers in the notion that space and time themselves aren't fundamental, but arise from a deeper substrate of quantum information or entanglement, an idea called emergent space-time. Usually, we regard space-time as the stage on which physics unfolds. Emergence flips the script. Maybe the stage is constructed from the play. In other words, entangled quantum states might weave the geometry of space-time so that distance and duration appear as secondary concepts. An analogy is how a 3D hologram emerges from a 2D pattern. You see depth, but it's encoded in a flat surface. Similarly, the holographic principle suggests our 3D plus time reality could be encoded on a lower dimensional boundary. Dig deeper, and you find proposals that geometry is just a manifestation of quantum entanglement patterns. The more entangled two regions are, the closer they appear in emergent space. This perspective might help unify quantum mechanics and gravity. Traditional attempts to quantize gravity treat space-time as a background that's diced up into tiny elements. Emergent space-time says we should start with quantum information and see how a gravitational metric arises. This approach resonates with the success of ADS/CFT correspondence in string theory, where gravitational theory in a bulk space corresponds to a quantum field theory on a boundary, suggesting geometry and gravity can be derived from purely quantum interactions. Experiments can't yet confirm emergent space-time, but certain black hole models and studies of entanglement entropy hint at how geometry could be knitted from quantum correlations. Tools like tensor networks in quantum computing provide conceptual examples. As theoretical frameworks expand, researchers test if these insights match known phenomena, from black hole thermodynamics to cosmic inflation. While still speculative, emergent space-time gives hope for a grand synthesis. Rather than a cosmic swirl of mass energy warping a static arena, we might see the universe as a dynamic web of entangled information, forging its own geometry in real time. To proven correct, it would topple centuries of thinking that space-time is the bedrock of reality. Instead, reality might be more akin to a quantum tapestry, weaving the illusions of distance, motion, and time from threads of entanglement, offering a mesmerizing finale to the search for a unified physical theory.